see how to go, because then there are the IPR related and many other issues.
Yes.
Yeah, but during the workshop, they can see basically. They can go on any speaker talk and then they can check. So if participants have any general question, they can ask us, because in 2 minutes we will start our talk. So if anyone is having any doubt during this session, you can ask, or in between we have gaps, so that time they can ask. So during talk also, if you have any doubt, you can raise your hand and then host will allow you. And if we will allow you, you can ask the questions at any time if something is not clear. And I request all the participants, you have to interact more with the speakers. So Nipun, can we start?
Yes, sir. Yes, sir.
Okay. So this one is connected with YouTube?
Yes, sir. Yes, sir. Yes, sir.
Okay. Okay.
So shall we start? 10 a.m.
Yes. I think some echo is coming. You have opened some another window also, so you can close, or you can
Is
keep
it
on.
fine now?
Yeah, now is okay. Now.
Okay, sir. Thank you.
Yeah.
A very warm good morning to all panelists, faculties, dear participants, and students. I, Nipun Sharma, student coordinator for this event, take the privilege of welcoming this virtual gathering to the fourth day of AICT Training and Learning Academy sponsored 5 days online workshop on nanosensors, which is being organized by the Department of Electrical Engineering, IIT Jodhpur from 5th to 9 July 2021. Starting with the event, I really feel honored and privileged BEL at IIC Bangalore. He has worked in Materials Research Center, MRC, from Indian Institute of Science, Bangalore. He has visited several countries such as Germany, Japan, and Singapore for his research works. He is a member of various scientific societies in India. He has hands-on training and 15 years R&D experience on design, fabrication, and characterization of micro-nano electronics and MEMS-based devices. He has indigenously developed piezoelectric films for MEMS acoustic sensors, and his developed sensors were utilized in Polar Satellite Launch Vehicle PSLV flights by ISRO. He has also developed indigenous bulk acoustic wave resonator technology for 5G and strategic applications. Moreover, he has published more than 90 journal papers in SCA journals and conferences. He is engaged in various sponsored research projects from several
Nipun, can you hear me? You are not audible. Nipun?
Yes, sir.
Yeah. Can you repeat this one, what you have said, last 2, 3 sentences? Because
Yes, sir.
yes.
His research interests includes piezoelectric, ferroelectric, and magnetoelectric thin films-based micro and nanoelectronic devices and sensors. Today, he will be delivering a talk on the topic, realization of nanoelectronic sensors. So with this brief introduction, may I request Dr. Jitendra Singh to kindly deliver today's talk for us. So please, sir, thank you. So over to you now.
Thank you, Nipun, for kind introduction. I'm audible?
Yes, sir. Yes, sir, you are.
Yeah. So, welcome participants in this workshop, ATAL Nanosensor workshop. And today I'll talk about the realization of nanoelectronic devices and developments we are doing at Sri Pilani. We'll discuss. So, our self-introduction, we are a CSIR laboratory and comes under the Ministry of Science and Technology, Government of India. So Sri Pilani is a national laboratory and the constituent laboratory of CSIR. CSIR has the 38 laboratories across the country and Sri Pilani is one of them. It is very old lab and established in 21st September 1953. And from then onwards, the work on the electronics devices development is going on here. And key contribution has given this laboratory to the country. Research work is mainly focused on the electronic devices development and the systems developments. And I myself belong to the semiconductor device development group. We have various groups here: intelligent systems group, microsystem packaging group, semiconductor device design group, fabrication group, societal electronics group, vacuum electronics group, and the vacuum electronics packaging groups. And it is the green campus of Sri Pilani. It is visible here. Today our outline will be the basic objectives for this nanoelectronics MEMS devices. What are the motivations? What is the background? Then we'll learn some fundamentals of the MEMS and the nanoelectronic devices. The current these are devices in market. So we'll see what is the current economic status of these devices and where they are, their market trends. This micro cantilever and the acoustic wave sensors we developed in laboratory we will discuss, and some magnetic sensor, mass sensor, some trends, and finally we'll conclude this talk. So why we work for the MEMS or nanoelectronics devices? It's always a trend to make a very small size, highly efficient, mechanical, electrical components, same, all the things on a same chip. It's possible with MEMS. Cost reduction with improved efficiency, it will batch produce these devices efficiently. We can reduce the cost and improve product and building materials, easily transportation because these devices are of small size. Easily we can pack them and transport. Of course, they consume very low power because the volume is small. High precision, small scale devices possible. Mainly based on the silicon because silicon comes out as a robust material, and we'll discuss how it has happened. Wide range of sensors, actuators, generators, transducers, energy sources, resonators, filters, oscillators are possible with the MEMS. You can see at the right side of this MEMS microphone. It is a very less than 1 mm by 1 mm packaged microphone. So these kind of small scale devices are possible. MEMS gyroscope is shown here, energy harvesting package devices with the electronic circuits, MEMS motors, this electrostatic comb drives, MEMS resonators. So these all possible with this new technology. If you can see old MEMS gyroscope, not old means at that time MEMS technology was not there. So this gyroscope is used to measure the angular velocity or acceleration. So conventional microscope of the size of the meters, but MEMS has made it possible to a small size device. Small size, low cost and low weight and high accuracy are the main features of this. And we can see here at the right side bottom, the MEMS gyroscope of MEMS based is of few mm by few mm. It's all possible with the nanoelectronics and the MEMS devices. So miniaturization is the driving force. So humans are in the size of meters, our hands are the size of 10 centimeter or so, our hairs of diameter nearly 100 micron, RBC of the size of 10 micron, or E. coli is less than 1 micron, this viruses of the size of 100 micron, 100 nanometer. So MEMS are the regime of nearly the 10 micron, 100 micron to few microns. And if the nano size, if we are going below the 100 nanometer, the nano regime comes. Here the things comes more interesting, material behaves differently. So MEMS technology is the technology to make the smart small structures with the dimension in the nano or micrometer range. It conveys the integration of multiple mechanical components, microelectronics, and construction of the integrated electromechanical systems. Integrating electrical and mechanical devices on the same chip is possible. Typical device has the very low mass, small footprint, and the high mechanical resonance frequency, which are desirable today. And these provide the high measurement and sensing efficiencies, which is the most desirable. So if you see the around this, what are the kind of devices, actuators, sensors, resonators, filters, ultrasonic transducers, hearing aids, sonars, transformers, accelerometers, various kinds of devices possible, which are used in the various applications like in the acoustics, surface acoustics, bulk acoustics. Biomems are coming because the small size use disposable devices possible with the MEMS and the flexible integrations. Optical devices, optical MEMS, microfluidics devices play key role nowadays. Chemical based devices, inertial sensors like your pressure sensor, accelerometer, gyroscopes are very interesting. So let us see the key definitions are useful here. The microsensors, which are the sensors realized using a microfabrication technologies. Microactuators are the actuators which are realized also using the microfabrication technology. Microsystem is a complete system realized using a microfabrication technology. And MEMS is a combined terms which micro electromechanical systems, formally very subsystem of subset of microsystem and often used as a synonym of microsystem. In Europe, they call it microsystem, and the US and the other countries they call it MEMS devices. So that is the basic difference. So the basic introduction of MEMS technologies enable the widespread diffusion of sensors, mobile and IoT devices, automotives, domestic use, entertainments. If you see a timeline in 2010, there were the few sensors were available for the sensing like ambient light, accelerometer, magnetometer. But after 1 year, the more added like the gyroscope and the proximity sensors. Further, the pressure sensors were RGB sensors were added. Further in 13, the temperature, humidity, Hall effect sensors were added. So sensors are adding day by day through the MEMS and the nanoelectronics device development by the industries working in this field and the research going on these fields. Then comes the heart rate and the fingerprint sensors, temperature. So these are the variety of sensors are coming under the development. If you'll see our smartphones, sensors are around us, but these are inside it, so small size we are not able to see. Our smartphone has the force sensor, humidity sensor, gyroscope is there. Image is rotating in this through this device. Proximity sensor, 3-axis magnetometers, microphones, whatever we are speaking, it is able to hear it. Pressure sensors, accelerometers, fingerprint sensors, temperature, light sensors, cameras, gas sensors, many more are coming because now health will be connected through your this smartphones, and many more things will going to add in this smartphones. All possible with this nanoelectronics sensors and devices. If you see a PCB circuit board of this smartphone, where they are placed, these MEMS based on nanoelectronics based sensors. Silicon microphone is there to hear the sound. Camera and the proximity sensor is there. Autofocus actuator is there. MEMS micro mirror is there. The frequency we are able to communicate is the 1800 megahertz or 900 megahertz. Use the bulk acoustic wave filters or duplexers. Switches they are using in the front end of communications. Oscillators are utilized, accelerometers, gyroscope, compass, pressure sensors, and many things are around us in this smartphone. The market of the MEMS is emerging very fast, and smart watches, glasses, cameras, and many more devices are adding to this consumer markets. So it is the MEMS and sensor shipment for the wearable devices in millions of units they ship. If you see our car in automotive market, there is large need of these MEMS-based small size sensors. Microphones utilized for the noise cancellation, accelerometer for the airbag deployments. When this collision happens, no, the airbags opens due to the collision with the due to the collision, some force is applied on this sensor that give the signal and the airbags opens. GPS and the inertial navigation systems, fuel in the controlled way, pressure sensors, silicon nozzles for the fuel injection, air conditioning pressure sensor, mass flow pressure sensor, accelerometer for the suspension control, brake pressure sensor, tire pressure monitoring. Now people are trying for the online tire pressure monitoring live on the dashboard. So these are all possible with the MEMS and nanoelectronic devices. Let us see the top players who are leading in this field and leading the MEMS market. Broadcom is a big company and producing these MEMS devices. Bosch, ST Microelectronics, Texas Instruments, Poro, and HP, NXP, Novels Electronics, PDK are the key names which are the market leaders, and they have the variety of components for this smartphone and the other electronic gadgets. If we'll see the device-wise, the MEMS packaging and the forecasting, the RF MEMS, acoustic and ultrasonic sensors, environmental sensor, optical MEMS, inertial sensors. So the RF MEMS segment is increasing very fast compared to the other devices. Inertial sensors, this market is nearly saturated because it is from long time in the market. But this total CAGR is increasing with the 16.7%, and the RF MEMS is increasing fast with the 35.1%. So it is a billion-dollar industry, and this MEMS microphone through which we are our sound, our voice is able to hear by this laptop or mobile phones. These are either based on the condenser or based on the piezoelectric base. So piezoelectric based devices are increasing very fast now. What we are talking about, how these devices are made and what is inside it, how they are able to sense it, how they are able to actuate it, that is important. So it is shown here a micromechanical resonator fabricated through a MEMS process product from the ST Microelectronics. So this device has some fixed structures called the MEMS anchors through which the device will anchor, and few will be the mobile parts which will provide us the sensing of this, actuation of this. Variety of structures are realized for the sensing or actuations. These structures can be made in silicon wafers. Single crystal silicon wafers are utilized here for the fabrication because of the stable properties, repeatable and reproducible properties. We'll discuss why silicon we use floating plates, bridges, micro cantilever beams, cross beams, spirals, springs. It depends on the requirement which type of structures need to be realized. Accordingly, the structure is designed, fabricated, realized, and packaged and utilized. So microsensor means the materials which are the main. This single crystal silicon is the base material because it is available, it is robust, it is well proven material because of the long time microelectronics and the VLSI process. And earlier the chips were made on silicon. Now the very easily with the silicon, these MEMS come in the mainstream because silicon was available there. Polysilicon, mostly isotropic semiconductor materials, silicon dioxide, accident, thermal and the electrical insulator, silicon nitride, aluminium, very good conductor. Some other materials for the vias and the filling, copper, gold, platinum, various polymers, ceramics, composites, piezoelectric material, or some other kind of material are integrated in the devices to make a working prototypes. Mechanical properties of silicon. Silicon is an excellent material from the mechanical point of view. Considering these silicons compared with the other material like the carbon or silicon carbides or silicon nitrides or iron or tungsten or steel or something, the yield strength and the hardness of this material. No hardness means the hardness tested using these materials using diamond tips using force methods. Young's modulus, their density and thermal conductivity. If the compare silicon comes at the excellent material, robust materials where through which the device are possible to realize. Therefore, mainly the silicon are MEMS based now coming the flexible and the other kind of MEMS devices also in the market. The silicon crystal is very important, and this device use the crystalline properties of silicon for the etching purpose. So orientation is like the 100 plane or 110 plane and 111 planes. During the etching of these wafers, we utilize their planes. And direction dependent or etching is possible with different planes because certain planes are very easily etched using chemicals, but others are not. So these are utilized to make these microstructures, and small size structures are possible in the micron or nano size. Fabrication process involve the micro machining process steps and the various materials depositions, patterning through the photolithography, and the etching of this device or lift-off process. Substrate mainly silicon, standard wafers are used, or silicon SY wafers are used for this realization. The process can be of surface micromachining where we do not etch the bulk backside of the wafers. Only at the surface structures are involved in the process, and substrate is not involved. Bulk process means that we involve the silicon wafers for the etching process. So in the if we see a fabrication process, if we see this, we have taken the substrate and we deposited thin films, and if we want to, this deposition is possible using epitaxy, like the MOCVDs are used for the epitaxy purpose. Oxidation, through oxidation layer, thin films can be deposited through sputtering the or evaporation, CVD or PCVD or LPCVD or sol gel. Any methods can be utilized for the thin films. Now this thin film need to be patterned. So the thin layer of photoresist, which is a light sensitive materials, is deposited. And this material is patterned using a system called mask aligner through a mask process, photo mask process. And certain area is exposed, certain not exposed, and this material is developed. So patterning is done through optical lithography or double-sided mask aligner. Then comes the step of this etching. So etching of this layer can be done using a wet etching process or wet anisotropic etching process or plasma or RI or DRI, depends on the device requirements. So these are the main steps for any kind of device involved in the fabrication. Etching of silicon. If you are going in the bulk side, the etching is kind of two types, wet etching or plasma based etching. And the etching can be isotropic or anisotropic. If it's isotropic etching and wet etching, we got this kind of profile. We have this no certain cuts, and the repeatability is not so good in this. In the plasma, undercuts are not so high, and is not give a uniform shape. But in the anisotropic, the silicon-based etching, if you do the direction-dependent etching, is possible between the 111 planes and the 100 planes. And these kind of structures are realized to make the diaphragms or cantilevers or some any kind of structures which we want to use. And with the DRI processor, these kind of structures are possible where the aspect ratio is very high and the vertical false formations are possible, which are the most desirable. So that the device will occupy a low space and that can be highly efficient and repeatable. So using this process etching of silicon, various chemicals are utilized to etch this, like the potassium hydroxide, EDP, ethylene diamine, pyroxatacol, TMAH. Our experience shows that the TMH is the most suitable and the less toxic compared to others. Here we can see some microstructures of the front side etchings. Grooves are made, or some membranes are made through the etching process. So, these are the hanging structures or the diaphragm structures, or some can be used for the pressure sensor. Some membrane can be made out of it. Deep reactive ion etching also used for this making structures, diaphragms, because control is there. Therefore, it is a costly process, but because of the good control, people prefer to make a commercial kind of device using the DRI. So, what are the steps involved? On the substrate, first the etch mask is applied. So, this can be some silicon dioxide or some photoresist suitable to device requirements. Second step is CF4 and polymer layer depositions, and the third step is again the bottom layer polymer edge, again the SL6 polymer layer and silicon. So these at the bottom you can see that these kind of vertical structures with the high aspect ratios are possible with the DRI process. Sensing and the actuations. How to actuate a movable structure by applying a force, and how to sense it. So actuation can be of many types, like the thermally we can actuate through the thermal expansion of the bilayer structures. We can do a piezoelectric actuation. So we apply AC bias across the piezoelectric material, and due to the piezoelectric effect, charge are developed and which give the force. Capacity where we can have the actuation due to the electrostatic force. Sensing can be of a piezoresistive through which the change in the resistance due to the stress is measured and the resistance variation is measured, monitored by the piezoresistor. Sensing can be piezoelectric where the force is applied and charge is developed. So these are the conversion of one type of energy into other type of energy in the actuation of sensing. Capacitive due to the capacitance variations, sensing is done. Capacitive sensing or actuations can be of two types, like that we can make a structure using a parallel plate where the two plates at the bottom and top will make a structures, and we can have a comb line finger structures for the sensing or actuation. If you see piezoelectric materials, there can be various types like the quartz or the aluminum nitride or zinc oxide or PZT. Here in our laboratory, we work on the zinc oxide because it has the good coupling coefficients, easily to produce the um, high thickness like 5 micron thick films are possible. And now in future, we are planning to develop the aluminum nitride films. This coupling is the measure of how much the electrical energy is converted into the mechanical energy. So at Siri Pilane, we developed the piezoelectric based MEMS devices based on the zinc oxide films, and we'll see what are the developments we've done here. We see a zinc oxide, it can have the three kind of structures. It can be a peroxide, zinc blend, and bauxite. This zinc blend and peroxide are the metastable structures. Bauxite is considered a robust and highly stable structure. Zinc oxide is a second of six binary compound semiconductors. It has direct band hexagonal structures where each anion is surrounded by the four cations at the corners of the tetrahedron. Here the lattice constant are shown here with the A, B, and C. A, B, and which are in the plane of the, and C is the perpendicular. And C by A ratio is maintained for these structures. So it's very stable structures. Space group belongs to P63Ms. For the piezo MEMS devices, both side orientation is desirable. In the both side orientation, the tetrahedral coordination enables polar symmetry along the hexagonal axis. And this polarity in the zinc oxide is responsible for the number of properties like the piezoelectricity. It says spontaneous polarization, means the polarization without any application of electric field. And key factor in the crystal growth, etching, doping, and the defect generation. The four common surface termination of zinc oxide can be zinc polar phase 001, O polar 001. Then can be C axis oriented of this, and non-polar phase can be 1120 A axis and 1010 M plane, which phase both contain an equal number of zinc and oxide atoms. Therefore, this A and M planes are not equal. The polar phases possess different chemical and the physical properties, and the oxygen polar phase possesses a highly slightly different electronic structure to the other three phases. The structures, it has the hexagonal wood sides, it is the molecular weights, lattice constants, density, melting points, band gap 3.37 electron volts, electric constants, piezoelectric coefficients. These properties we utilize to make a MEMS device. We'll see further how we. The first device we have done here, the film bulk acoustic wave resonator. This is the key technology, and is very useful because it is a breakthrough resonator technology. The performance possible using this technology is not possible by any other competing technology like the surface acoustic wave or some ceramic based resonators. This is used in the frequency shaping, the filters and the duplexers. This provides the high frequency operation, better performance, small size and low power. We can see here the silicon wafer which is etched from the back side of it, and the wafer thickness is nearly 380 micron thickness. Then silicon dioxide on it, and the bottom electrode on it, and the piezoelectric layer deposited on it, and the top electrode on it. We'll see how we realize this device. The piezoelectricity refers to the involvement of the concept of positive cations and the anions moving in opposite direction under the influence of mechanical forces. So this is the piezoelectricity principle. A mechanical deformation stress is applied across the crystal, then the electric dipoles are generated due to the shifting of anions and cations and provide the potential difference. How does this resonator works? This resonator realized based on the piezoelectric effects. When the external potential is applied across this piezoelectric layer, this produces internal mechanical stress. And this initiates the bulk acoustic wave that propagate through the elastic plate in the thickness mode direction. And the material converts some of the electrical energy into the mechanical energy and into the mechanical in the form of acoustic waves.
Your slides are not visible, Dr. Jitendra.
Again, I'm sharing. There was some issue, I think. Again, I'm
Yes,
sharing.
yes, please.
Here we were, and now it is audible. Hello.
Yes.
Yes. So piezoelectricity, and there are it is based on two relations. One is related to the direct piezoelectric effect, and one is the converse piezoelectric effect. T is equal to Cs minus E. We know it is the Hooke's law. T is equal to Cs, but for the piezoelectric, it is a modified Hooke's law. So emergence of stress associated with the presence of external electric field due to the dielectric piezoelectric effect is called that. This first described by the first piezoelectric equations. And second equation includes the inverse piezoelectric effect creating the electric displacement when a strain is produced in the materials. So this bulk acoustic wave device we utilize the inverse piezoelectric effect. Material aluminum nitride, we utilize the stiffness of these materials, this electric displacement and the permittivity of the material, piezoelectric constants, the main properties we utilize to design and fabrication of the device. There is some simulation be done using a finite element methods and seeing the resonance and the anti-resonance of these bar devices, which are seen at the 1.1 gigahertz applications. How to realize this device? We start with the silicon wafers and the growth of silicon dioxide, then the growth of the platinum bottom electrodes, then we go for a deposition of this zinc oxide layers. At the left side, we see this top view, and the right side, we see the cross section of this. So patterned zinc oxide layers we can see here in the yellow color, and each layer colors are shown at the bottom of this page. Then the platinum deposition and the patterning of it, and at the top side around the resonator, we open a window and we release the structure through the backside bulk micromachining process. So this is the process how we realize this and how we work in the lab. Seeing the colors on the wafer is very important, and by seeing the colors on the wafer, you can tell that what is the layer deposited on this. Because colors is dependent on the deposited material. Each material has a specific colors. So we can see at the wafers, we start with silicon wafer, then degreasing, planing, HF dips for the this oxide, the native oxide removal, then we do the oxidation of nearly 1 micron thickness. After the oxidation, wafers colors look like some violet colors. Then we do the lithography one for the bulk micromachining process, and we do the buffered oxide etching process through the removal of the silicon dioxide. Then comes the backside etching of this, and after and this setup is seen here, the etching setup, and the wafers are etched from the backside have the open cavities we can see here. Cavities, if you see in the microscope, it looks like as we see in this window. then the patterning of bottom electrode, then the deposition of the titanium gold, then lift-off process, and the deposition of this zinc oxide, and we can deposit 6-inch wafer. Here we can see the 3-inch, 3 wafers at a time we can deposit. But from the ISRO we receive 6-inch wafers and we are able to deposit the 6-inch wafers. The lithography, we can see that it is kind of zinc oxide is slightly yellow color films, and we can see here the etching of this zinc oxide. Wet etching is done. Wet etching is done. Finally, the top electrode depositions, and the top electrode deposition, and finally the resonators are realized at the wafer level, and each device under the microscope looks like this. The bulk micromachining setup, we established a facility here for this realization of devices. These include the jigs and etching setups in which the stress engineering we done for the zinc oxide films, and we established a low stress zinc oxide films using this sputter process. We done the sputtering at the wafer level of various pressures like this. We found that the sputter pressure is the key parameters to influence the stress in the films. But at some pressure, the minimal stress we found and the low stress films were established. Our films, grown films at the room temperature are the single phase films and do not contain any impurity films. So these are the highly C-axis oriented films are established with this machine. The structures we see in the process, the scanning electron microscope image, we can see here the square wave resonators, pentagon resonators. This actuation of these resonators were performed using the laser Doppler micrometers. So these are the piezo-based devices so that we can excite through at the ground terminal and the source terminal, and due to the piezoelectric effect device actuates. So these are we monitor the displacement in the picometer range and the frequency. So displacement was monitored, and this was plotted with the mechanical resonance for the square and the pentagon resonance. The phase change was observed at the resonance, mechanical resonance frequency. Also for the pentagon type resonator, the phase change was observed at the resonance frequency. In the square we observe 2 modes, but in the pentagon we observe only a single mode of the resonance. Then we done the microwave characterization of these F-bar resonators. We place them in the package of RF package. We using SMA connectors. We can see wire bonding of the device, and this consists of the silicon, then silicon dioxide, and then the bottom electrode, then the zinc oxide and top electrodes. And these are some Smith charts, and the scattering parameters were measured using the vector network analysis. This device was actuated using how does it actuates with the applied AC electric fields. Hope you are able to see the actuation of the diaphragm we have made here. It is actuated with the applied biasing electric fields. So it is a live device. Working prototypes we demonstrated at the lab level. Prototypes of these devices are developed, and we are under the development of commercial scale devices at this moment. So these are the structures made in the laboratory using consist of various layers. And right side we can see its electrical performance, where impedance is plotted with the resonance frequency. And resonance was series resonance frequency was 0.99 gigahertz, and the parallel resonance frequency was 1.00 gigahertz. So it shows that it is working at the 1 gigahertz resonance. And now this has to be converted into the filters. We made this resonator into the form of a tunable resonance. That tunable means the center frequency of this resonance can be tuned. So integrate a magnetic material inside like the iron cobalt at the top electrode. We integrated the meters. So iron cobalt films the magnetization versus the magnetic field plot is shown here. It is saturated nearly the 3000 hours per electrode. This F-bar resonator was placed in the magnetic field and the live magnetic field was measured using a Gauss meter. Resonance frequency was measured using a vector network analyzer and this setup we use the magnetic field we develop in indigenously in our laboratory. The fabrication we done discussed various steps are included from the silicon wafer to the conversion to final step. The measured performance, the return loss of these devices were measured with without any magnetic field and with the field. So with the field, we have observed the frequency shift of nearly 106 megahertz. So it is a very high quality factors resonators. Then the modeling of it and the modified Butterworth one device model was utilized to model this behavior and the circuit parameters were extracted. Fitting was done without magnetic field and with magnetic field. Experimental data and the MBVD model fitted data are compared. These are some other results of this device using their this capacitance with the voltage, their material performance, low tangents, and the armature. The next device we worked here on the piezoelectric MEMS based mass sensor. Micro cantilevers were developed and then these are actuated using the AC electric field. These cantilevers consist of this silicon dioxide, then the platinum, zinc oxide, and the top layer. And the mass loading layer again was your zinc oxide layer. And this deflection of these cantilevers was monitored using a laser Doppler micrometer, laser beams. So it is a schematic cross-section of this micro cantilever based mass sensor. The process steps were similar as we discussed, starting from the silicon wafer to the final device realization. Again, the very high quality zinc oxide single phase films were utilized for this deposition. Low stress zinc oxide films of nearly 40 megapascal were utilized for this. At wafer level, these stress measurements were performed using our lab equipment, and that is based on the Stoney's equations. The etching profile of zinc oxide is very important to make a good step coverage. And we can see here the various layers and they are at the different magnifications and the angle between the figure C, we can see angle between the zinc oxide and the SiO2 layer was 59.36 and with the thickness of 1.5 micron hidden layer thickness. So this do not provide, when we provide a top metal layer on top of it, this provide the discontinuity here. How to avoid discontinuity, then the stock coverage has to be improved and this profile has to be improved. So those experiments we have done and the metal patches and the discontinuities after the metal layer deposition we can see. So these experiments were done and finally the release of array of micro cantilevers were realized here. We can see an array of these micro cantilevers, then the single 300 by the 60 micron length micro cantilever were realized and the top view of array of micro cantilever for various sensing applications and the tilted view of this. This consists of a layer of stacks which consist of your bottom electrode platinum, zinc oxide and the top electrode and these are the bias pads are extended to bias this, actuate these cantilevers. This can be used for the various applications like your mass sensor or your gas sensor or some other kind of sensors. So these are some resonance frequency versus the cantilever length. As the length increases, the resonance frequency down because of the high loading. Deflection of this cantilever also increase with the cantilever length. Deflection with the DC actuation volts. For the small length cantilever, deflection was less. As obvious, the cantilever length was increased, the deflection was more. So this is the deflection versus the frequency plots for the various micro cantilever structures, and the frequency shift was observed. Highest sensitivity sensor was realized using a 100 micro length cantilever because of the high quality factor. What is the sensitivity of this? Sensitivity is defined as the frequency shift divided by the loaded mass, measured in the hertz per picogram. So it is a highly sensitive sensor, and we reported in the JMM this paper. And as the micro cantilever length is increased, the sensitivity was decreased. So mass sensing performance was decreased, was high for the smallest length micro cantilever. And we compared in this table the various length micro cantilevers and their size, resonance frequency, their frequency shift, loaded mass, and the mass sensitivity. So best sensitivity was observed 0.3138 for the hertz per picogram for the smallest micro cantilever. Now this we can see here a 3-inch idealized wafer. These cantilevers are made, and these are the array of cantilevers have been made, and its size of one cantilever is 180 micron by 580 microns. Magnetostrictive are the materials which change the size or length elongation when the magnetic field is applied. So this figure shows a 3-inch diameter wafer along when the die is using the laser dicing. Device yield was 100% as visible in the device. So magnetic actuation experiments were done using these microcantilevers. Some stress engineering for the low stress measurements, and the stress was compensated using the SiO2 and iron cobalt bilayer combination. We know that the silicon dioxide has the compressive residual stress. That was compensated using iron cobalt layers, which has the tensile stress. And this setup was the laser Doppler vibrometer was used for the characterizing these structures. Samples placed under the object and scanned using the laser interferometer. Magnetic field was applied during the magnetic measurements. As we can see in the figure B, magnetic field was adjusted by the moving magnets in the tray. And customized this setup was in-house made, and the magnetostriction coefficient was measured for these iron cobalt layers. These are the actuated and using a piezo disc made of PZT materials. These microcantilevers were coated with the magnetic material, and their actuation was performed in the presence of magnetic field. So cantilever amplitude and phase was measured using the laser Doppler vibrometer which was measured in the nanometer range, as we can see, and the resonance frequency was nearly 26 kilohertz, and the phase change was observed at the resonance. This we utilize in the form of a magnetic sensor, this micro cantilever based MEMS magnetic sensor. This consists of various layers like the silicon dioxide, platinum, bottom electrode, zinc oxide, top electrode, and the iron cobalt layers. When the magnetic field applied to this micro cantilevers, they deflected due to the strain in the magnetic layers, which deflect these micro cantilevers. And these are based on the magnetoelectric effect, and due to the strain in layer, the piezoelectric material will actuate, and that voltage will be developed, magnetoelectric voltage. So output voltage is measured when this subject to magnetic field, and the sensing performance is seen here. This consists also of various fabrication process steps, like the starting from silicon wafers, micromachining, patterning of electrodes, then the piezo layer deposition, then the electrode magnetic layer deposition, contact pad open, and the sensor realization. These are the some devices we developed for the DRDO, released micro cantilevers, and 3-inch wafers we realized. The bottom side we can see a packaged MEMS magnetic package size. It is die size is 7 mm by 7 mm. This These cantilevers live actuate in the presence of magnetic field recorded using a laser Doppler biphotometer. Live actuation of this cantilevers is visible here. It is recorded using a LDV here in Silipilan. Stress analysis of this is very important to realize these structures, and it is very important to make a low stress compensation also done sometime. This journal-based energy harvesters and energy generators are also very important. These nanowires and the other kind of structures are also reported for these kind of materials. This shows that some TEM image of nanowires and how they are probing these nanowires and making their electrical and the transport measurements. Some of the studies of these for the Schottky barriers, piezoelectric nanowires, and this coordination system is reported. At Siripilane, we have the under a single roof a huge facility like the sputtering, some mask making, PCVD, etching, some mask aligners, active etching, laser dicing, saw dicing, metallization, implant diffractions, VSM, PL, and many more FSMs, DECTEC. So in summary, today we'll learn about the fundamentals of the piezoelectric based MEMS or nanoelectronic devices, their current trends, piezoelectric materials, processing of these MEMS devices, magnetic sensors, acoustic wave resonators. Many people help us in these projects and their execution. Our semiconductor teams and various projects help us to carry out this research work. Various things are taken from these references to make this presentation. Thank you for your attention.
Yeah, thank you, Dr. Jiten Singh, for excellent talk. And Nipun, can you take the questions from
Yes,
chat?
thank you, sir. Thank you for such a nice talk. The first question is from Mr. Ashok. He is asking what is the cause for the oscillatory response of the electrostatic MEMS cantilever beam when it is released before it settles? Answer.
So what he wants to know, can you repeat, please?
Yes, sir. So he is asking what is the cause for the oscillatory response of the electrostatic MEMS cantilever beam when released, that is, voltage is removed before it settles.
So if any electrostatic force is applied, then this has to actuate because between the capacitor is made because one electrode is applied on your cantilever beam and one at the ground level. So electrostatic force is applied between the two plates. So plate will move, but there's some through mechanism it has to be controlled.
Okay, thank you, sir. Another question he wants to ask, like, is there a way to avoid or limit chromium diffusion through gold and surface oxidation in chromium gold thin films?
Chromium gold, usually the chromium, in place of chromium, you can use titanium, but chromium and titanium both are the very adhesive material. Diffusion in the case of zinc oxide, what we have done to stop the diffusion, we apply a small layer of PCVD silicon dioxide. So PCVD, that is the interposer layer we call. So interposer layer do not allow these chromium layers, chromium atoms to diffuse in your functional piezo materials. So that is the solution.
Okay, thank you, sir. We have another question from Tarun. He is asking how the amplitude of vibration of cantilever is related to its dimensions.
Okay. So L to the, as per our cantilevers, we established L to the power, the sensing we established for this cantilever. sensing was anti-proportional to the length, but the amplitude here, deflection amplitude increased with the cantilever length, and some relation is established. I can share later. I can share the relation. What is the actual relation we established? Yes.
Okay. We have one more question from Mr. Amit. He is asking, what do we do to reduce stress in MEMS devices?
Yeah, you can control by layer deposition. You can control the process parameters so that this process parameter will allow your films to settle down the atoms. And one way is to process parameters controlling. Other way is to, like, your film may be compressive or tensile. To adjust the stress, opposite stress layer, you can combine with it, and if your layer is compressive, before it deposit a tensile layer, so that a stress compensation is made, and you can make a low stress or some your process parameter controls. Yes.
Yes, thank you, sir. With this, Mr. Sudhir, I guess he has raised his hand. Please allow me to unmute him. Hello, Mr. Sudhir. Hello. Mr. Sudhir, you want to ask some question? No, sir, he's not here. Okay. I guess we are done with question and answer. I cannot find any more questions. Professor Mahesh, sir, you can proceed, sir.
Yeah, thank you very much, Dr. Jitendra Singh, for this excellent talk here. And yeah, if participants, if they have any other general query, they can ask. Otherwise, we will take for the break around 25 minutes. And next speaker is Professor Ramesh Chandra. He will join at 10:25. So we can, sorry, 11:25. So we can start the next lecture from 11:30. Yeah, thank you, Dr. Jitendra Singh, for this excellent talk. And basically, yeah, I would like to inform this one participants. Siri is doing the complete packaging of the sensor. So if you are interested, basically, they also have the academia and industry collaborations. You can use their facility, you can collaborate with them, you can write them, and then you can utilize. I think in the northern region, this many this one institutes, they are using their facilities. They have very good fabrication facilities. Dr. Jitendra Singh has shown different MEMS and different structures. That fabrication is not possible because required the different this one is steps of lithography, deposition, because they are optimizing each layer this one and doing at the large scale. So thank you, Dr. Jitendra Singh, for this nice talk.
Sir,
thank you, sir.
Sir,
we invite the highly motivated people are invited to come to Siri, and anytime they can interact with me if they have the research interest.
Sir, we have one more question that has just come up. May I ask, sir?
Yes, we have time.
Yes, yes, sir. It's from Mr. Sumit. He's asking, what is the effect of temperature during acoustic sensing or for acoustic sensors?
Okay. As the temperature of the device is increased, suppose for a piezoelectric materials. So due to the TCF, temperature coefficient of frequency, it will change. So there will be small drift in the resonance frequency due to the temperatures. So usually with the high temperature, it expands, and the Young's modulus of this material will change. So the Young's modulus of this material directly related to the resonance frequency. So there will be some shift will be observed. Yes.
Yes, thank you, sir. I hope it is clear now.
Thank
yes, sir. Yes.
Yeah, thank you, Dr. Jitendra Singh. Now I think we can take a break.
Yes, sir. Yes, sure.
Yeah, so next talk is at 11:30. So please join at 11:25. Okay, then. Thank you.
Okay, bye.
Yeah, Nipul?
Yes, sir.
Yeah, so Professor Chandra will join in 5 minutes.
Okay.
Yeah, some technical issue. So he will be here after 5 minutes.
Okay. Okay.
So I request all the participants, please wait for 5 minutes. Professor Chandra will join in 5 minutes. Meanwhile, if you want to ask some general questions, you can ask this one if some doubt or any feedback about this workshop.
Hello.
Yes, Tarun, you want to say something? Yeah, please.
Yeah, Mahesh sir. Myself Tarun, and I am a faculty in VIT Department of Physics.
Okay, okay.
So, if you remember, I told you other day, Jay Narayan and Nitin were my batchmates in IIT Bombay.
So I'm successful.
So actually,
Yes,
Finally.
yes. Tarun, we will talk this one after this talk. Yeah, good morning, Professor Ramesh Chandra. Can you hear us?
Yeah, I am just able to hear, but this very feeble sound is coming. I don't know, is this problem from my side or from your side?
No, no, here your voice is clear. We are not getting any voice. Please check if some other window is open.
So now you please allow me to share.
Yes, yes, sir. Nipun.
Yes, sir. I have already passed on the presenter privileges to him, sir.
Okay, I think I have to go to my open system preferences to share.
Yes,
Allow
sir.
WebEx event to record your computer screen so that you can. Okay, okay, just wait.
So I guess somehow he is logged out. Maybe he will join again.
Yeah, we will wait for 1-2 minutes. Otherwise, I will call.
Yes, now I can share.
Yes, we can see now. Yes, fine.
So, can you see it now?
Yes, yes. Yeah, perfectly fine. Yeah. So, Nipun,
Okay. So first of all, actually, this last week my this iMac got crashed, so I have to reinstall. So yesterday I was doing this whole these things. So I am able to do it. And so I was just rearranging my talk. So this is not very well organized. So but whatever work has been carried out at my the center, so I will just share with you. So I can start now.
Nipun, sir, 2 minutes. Yeah, Nipun, can you start?
Yes. Yes, sir. So moving on, I really feel honored to welcome our next speaker, Professor Ramesh Chandra, who is currently the professor and head at Institute Instrumentation Center, IIT Roorkee. Professor Chandra received his MSc degree in physics from AMU Aligarh in 1987 and PhD from National Physical Laboratory, New Delhi and IIT Delhi. His research interest lies in the experimental condensed matter physics and nanostructure thin films by physical vapor deposition. Known for his expertise, he has established state-of-the-art nanosciences laboratory at Institute Instrumentation Center to synthesize nanostructure materials by PVD processes. Most of these facilities have been designed and developed in-house to promote the Make in India concept of the country. For such an outstanding academic contribution, he has been honored with several awards and recognitions, such as Dr. A.N. Chatterjee Memorial Award on high TC squares in 1990, visiting scientist at TIFR Mumbai from 1997 to 1999, Commonwealth Fellowship at University of Cambridge, UK, INSA Fellowship to visit Poland Academy of Sciences from June 7 to June 28, 2019. He has published 200 plus research articles in peer-reviewed journals, 125 plus international conference proceedings, and guided 26 PhD students so far. He is also the member of several technical expert committees. Some of them includes DRDO, Indian Institute of Petroleum, CSI at Dehradun, Inter-University Accelerator Center IUAC, and Indian Oil Corporation Limited, Faridabad. Today, he is delivering a talk on the topic 1 and 2D structures for energy storage devices, supercapacitors. So I once again heartily welcome Professor Ramesh Chandra sir to request formally to deliver today's talk for us, sir. Thank you, sir.
Okay, so thank you very much, Mr. Organizer. Actually, I couldn't get your name. So
Nipun, it's Nipun Sharma, sir.
Nipul Sharma.
Nipun Sharma.
Nipun.
Yes,
Okay,
sir.
okay. So
Yes,
Professor
thank you,
Nipun Sharma, thank you very much.
Sir.
So it's all
And
right, because here, even if you are assistant professor, we call them as a professor only.
Sir, sir, I'm student. I'm working under Dr. Mahesh, sir. I'm a research scholar.
Great.
Yes.
But you look like a little senior. So I thought it must be at least assistant professor. Okay.
Maybe.
Anyway, you will be in future. You will be assistant professor. So no problem in that. So thank you very much.
Thank you so much.
So this today's talk is not very well organized due to certain technical reasons. So, but please excuse me for that. I will just skip some of the slides which are not relevant for today's talk. So this talk will be related to only this nanostructured materials for energy storage devices, and that too, especially I have already mentioned, it will be supercapacitors, not on batteries. So, but definitely I can share with you, we are doing differently what the others are doing in the country or across the globe. So that I can you can get rest assured that you will get something new. So I will just start with this kind of like introduction types of capacitor, supercapacitor, history of supercapacitor. I will not go. Supercapacitor versus battery, just one slide. Then types of supercapacitors, applications, current specs, requirements, and mainly I will focus on the results from Institute Instrumentation Center IIT Roorkee group, which is my group who is working on this area for last 7-8 years. So I will share all those interesting results which we have got at IIT Roorkee, which you will, I hope that you will, I'm sure that you will love it. So first of all, why we need this energy storage and what is energy storage? So this energy storage means basically the conversion of excess electricity into a different form of energy, which can be reconverted into electricity with minimum losses. Like, for example, we wanted to utilize the energy from the solar cells. So that you know that the sun is not throughout 24 hours. So during night, if you wanted to use the electricity, then you have to make some arrangement to store it. And that should have a lack of some efficient mechanism. So it should need to reduce the gap in supply and demand of electricity to compensate for temporary loss of production, a spike in the peak demand of energy supply. So sometimes you need more energy compared to all the like during daytimes. Morning you may not require that much of energy compared to this afternoon demand for this AC electricity for running in various electrical devices. So then this energy can be of like we can also use this renewable energy sources, which are basically this non-constant energy generation, large installation setups needed, and these for this is specifically for renewable energy sources. We need to have very good storage mechanism. So that therefore we need to have very high quality this different type of storage sources like batteries, so this fuel cells or some other devices like on supercapacitors, which can store the energy for the peak demands. So the energy storage devices can be divided into this 3-4 categories. The fuel cell is one, supercapacitor, battery, and conventional capacitors. So as you know, this conventional capacitor doesn't retain this for too long. So therefore, we need some supercapacitor which can have much higher power density and energy density compared to the conventional capacitors. So if you just see the comparison between these capacitors and batteries characteristics for their power density and energy density, you can see here the capacitors have very high power density, but at the same time their energy density is very, very low. While the battery are in opposite, like battery have very high energy density, but their power density is very small. So suppose you require very high power power at a certain instant for like acceleration or all those things, then battery cannot sustain those kind of power requirements. So for that you need some other device which can deliver instant energy at that moment. So for that we need like supercapacitors kind of a device. So current status of the supercapacitor devices, like they are approaching towards this power density of the like conventional capacitors and power energy density of the batteries. But we need our focus in future is that it should go much beyond. Like they should have very high power density and very high energy density both. So this is the current demand. So these are the like typical capacitors you can see here. And then if we just wanted to compare between a supercapacitor and battery, so you can just see here, the supercapacitor is just you can see like a when you have to run very fast, like you have to do a sprint, like Usain Bolt in Olympics for 100-meter race, and while for batteries, it is just like a long race, 5-kilometer marathon. So for that you require very high energy density. But for this 100-meter race, you may not require very high energy density, but you require very high power density that you can immediately pick up the speed, very high speed. So that's the basic difference between this supercapacitor and battery parameters. So if you just see here, like specific energy for supercapacitors, it is 1 to 5 watt-hour per kg, while for batteries it is much higher, the energy density. And if you compare this specific power, means energy density, power. So this is like 1,000 to 10,000 watt per kg, while this is much smaller in case of batteries. So, and charging and discharging time, this is also very, very important. Charging time is 1 to 10 seconds, while for battery it is much higher. So self discharge at room temperature little high, so compared to batteries. So these are some of the positives and negatives. Or lifetime or cyclic stability is much higher for capacitors compared to these batteries, so which are having low cyclic stability. And then storage mechanism is also very different. Like in case of supercapacitors, it's a surface phenomena, while in batteries, it's a bulk phenomena. So this limited storage capacity because of this surface phenomena. So therefore, they have low energy density. While in case of batteries, they are more surface area available to accommodate ion, high energy density arises because of that. So this electrode electrolyte interactions very fast. So no chemical reaction involved in high power density in supercapacitors. While in case of batteries, it involves chemical reactions, slow electron transfer, low power density because of this reason, that low, because of the slow electron transfer. So their power density is low compared to supercapacitors. So I hope this is the basic difference between these. I can explain it. So now the supercapacitor or then types of supercapacitors like you can have compared to this. First of all, like types of capacitor. This is a simple electrostatic capacitor, which is also known as conventional capacitors. And then comes this electrolytic capacitor or then supercapacitor. So these are the basic configuration of these three types of capacitors. But I will not go towards all these details. So this is all available in the literature. So, but I will just show you that why we need the supercapacitors. I have already told you that for certain applications, we require instant power density, very high power density. So therefore, where batteries cannot work, or there are some fluctuations in power fluctuations and some transmission lines or some other requirements. So there also you need something to regulate that. So for this, you need a device which can instantly get charge or discharge. So that is only supercapacitor, not batteries. So therefore, so this is like storing a small amount for short time, fast delivery. So we need a capacitor, but if you just increase this, then we need a supercapacitor for major storage for long time. Slow delivery, we need rechargeable batteries. So this is the basic requirement for a supercapacitor. Like in case of car, when we are accelerating, we need definitely we need a electric cars. We need a supercapacitor so that it can deliver immediate instant energy during its acceleration. Though it will later on it will charge because it is discharged very fast. So it will charge again with the help of battery only. But battery cannot deliver that power which is required at the time of acceleration. Similarly, at the time of when you are applying a brake, so you can just regenerate that power through traction. So you can recharge it. So now this is the history basically of the supercapacitors. You can see here. In 1995, the supercapacitors were used for electric cars. So Russia has used this for electric cars, these supercapacitors. And then in around 2004, Shanghai High-Tech Park developed a fast charging system along with the fast supercapacitors bus in the world. So first time they had run this electric bus in 2004 in China, and 2006 the first commercial bus line in Shanghai again. This 11th was launched. This again they had made number of buses to run on this commercial, this like supercapacitors and batteries. So this in 2009 the supercapacitors were developed for hybrid electric vehicles by nanotechnology. At that time, around 2009 2010, but more recently, now we need flexible supercapacitors for various applications for wearable electronics and all those things. So like in 2018, so flexible supercapacitors were jointly developed by Russia and Finland. And 2019, the rechargeable supercapacitors were developed by United States. So this is the basic history of the supercapacitors. And then these are again some comparison with various storage parameters. So again, I have already told you that their discharge time is much longer for batteries. Electrostatic capacitors, it takes a few seconds, only less than a second, while supercapacitor takes 0.3 like 30 seconds. But charging time is 1 to 5 hours for battery normal. And for electrostatics, it takes less than a second. And for supercapacitor also takes few seconds. So this is the charging discharging characteristics of battery and capacitors. And then again, this energy density is much higher for batteries and much lower for this supercapacitors. But specific power, just compare here this with the battery. This is 50 to 200 watt per kilogram, while for supercapacitor is 1000 watt per kilogram. So this is much higher. And similarly, the cyclic life. This is also much better for supercapacitor compared to this batteries. And the advantage of supercapacitors are the ability to store and release the energy. So these are just related to those parameters only. The other thing is like supercapacitors can operate in wide temperature range. Like you can operate them in -25 to 50 degrees centigrade. But while this is not the case, same is not the case true for batteries. It may not be possible for batteries to operate at much lower temperature and much higher temperature. So these are some of the basic parameters for supercapacitor, defining supercapacitors, like their energy density, which is defined as the capacity to store energy per unit mass or volume and is calculated by this formula. While for power density is the ability to deliver the stored energy and calculated by this formula. While electrochemical impedance spectroscopy is used to calculate the capacitance and internal resistance, where specific capacitance is measured using this relationship. So now I will just skip this. Okay. So this is now the supercapacitors are governed by the same fundamental equations as conventional equations, but utilize higher surface area electrode and thinner dielectric to achieve greater capacitance. So this is the major difference. And now this is again some of the applications for this supercapacitor where you require to regulate the transmission line to grids and to store wind energy, to store solar energy, and to use them in like in display devices, or you can use in this for charging. You need, because if you start charging using only this battery, so it may take several hours. So you cannot wait while we are traveling from Delhi to Roorkee, for example, takes normally 3 hours or 4 hours. But if you have to take like a petrol or so it takes hardly a few minutes at the petrol station. But you start charging, and the charging is totally entirely dependent on battery. So it may take hours. So that you may not like to have. So for this, you have to enhance their charging capacity of these electric vehicles with the help of capacitors, so where the supercapacitors are in demand. So that is the requirement. These are the current specs nowadays available. The different groups have made, like TK group SC series of alpha capacitors are rated up to like 150 farad. Probably earlier you might have just heard the capacity of a capacitors in simple capacitors, conventional capacitors. They are just microfarad or picofarad. But nowadays they are available up to 150 farad of capacitance. So you can just imagine, and that voltage is up to 2.7 volt. And the maximum peak current can be up to 65 ampere. So you can just imagine that they are the kind of change has taken place in supercapacitor technology, that they had gone from picofarad or microfarad to several hundred farads capacity. And these are some of the other applications where you need a flexible supercapacitor nowadays for wearable devices and some other devices. And then in day-to-day life, there are various ways where mechanical energy just go as waste or generate jet heat. So the same, if you can develop this flexible supercapacitors, so all those energy can be converted into electrical energy by using some mechanism, by just converting this mechanical energy into electrical energy using this supercapacitor devices, which are having this flexibility and all those things. So these are some of the examples related to that. So okay, now come to my group, where this is actually, I have already shown this in my earlier lecture also, that this is my lab. I only work on this physical vapor deposition technique, where I use pulse laser deposition system, excimer laser, various sputting systems or evaporation systems. All these are available in my lab. And all these facilities have been developed with the grant which I received from different funding agencies. And all these students are trained. And this, whatever chambers you see over here, they had been designed by ourselves as per our requirement. That you can see somewhere we are having like co-sputting chambers, and some chambers are like and this is for nanoparticle synthesis, and this is for industrial sputting system where we can deposit large area, and there are some other systems where we can have multi-layers, like the sputter sources are just one by one, and here they are coaxially implanted inside this so that you can do co-sputtering. So this is again depending upon our requirement. We just design and ask our fabricator in Bombay to provide this kind of chambers. So all these students are trained on these facilities so that wherever they go after this completing their PhD, then they can develop their own lab or help some other group to develop their laboratories over there. So they are all doing very well wherever they had gone, even abroad or here. So this is my XIMA laser system. Here I am having this two sputting chamber, so two deposition chambers for oxides and one for metals. Now comes, like as I told you that I'm going to deliver a talk related to this low dimensional nanostructured materials for energy storage. So for that, how to make, first of all, this thin film are always already in 2-dimensional, but in addition to that, we can make 1-dimensional materials also, like nanorods or nanotubes. So by that, we just modify our synthesis techniques. So first, what we do normally, we before deposition any material on our substrate, we normally do the electrochemical anodization just to make these porous structure on our surface of that substrate. So this is just an example of silicon substrate. Before deposition of any material, we just anodize it in a homemade setup, and we create this kind of porous structure in it. So this surface shows here the top surface area of your substrate. This is 1 centimeter by 1 centimeter substrate, and then we just break it and take the cross-sectional SEM view. So you can just see that these pores are not just on top of the surface only, they just go deep inside, at least up to 50 micron deep inside this substrate. So you can just imagine that surface area has been enhanced many-fold compared to the simply 1 centimeter by 1 centimeter. Now you have this lot of pores available, and they are deep inside. You can calculate the area. It can be very large compared to the bare without this porous structure. So this is, and then we deposit material on this. So I will, also this changes this kind of structure. Once you create this porous structure, this changes the physical properties of your substrate surface itself, because before creating this porous structure, your this substrate is hydrophilic surface, but after the anodizing it, it becomes super hydrophobic. So this is the additional advantage for this structure, so that there will be no humidity condensation and all those things. If at all any condensation is there, so they will simply just will not be affected. The surface property will not be get affected by the humidity and other conditions, because this will not go inside it, and it will just slide down from the surface. And then we use sputting technique. By you cannot fill this material inside these tubes by any chemical route, because for that you have to apply some mechanism, and they should be through. Only then you can allow to pass through this fluid inside it. Otherwise, I have shown you that they become super hydrophobic, so no fluid will penetrate inside this porous structure. So only this sputting technique, which is highly energetic, which is a atom by atom deposition. So atom just directly go with a very high energy, 2 to 3 electron volt energy is associated with each atoms. So they just go inside it and just can reach at the even up to bottom. So this is again the top surface after deposition of this material, which has been deposited PDMG on the silicon substrate. And then this is again I have broken this substrate and then seen this cross-sectional SEM of that sample. So this shows that how the material has gone inside this. So this is how we deposit using this. So this is before and this is after deposition. So you can see the clear demarcation that how we can fill that material inside it. And once you deposit this material, you can just see here yourself they are simply sort of nanoparticles inside this very large area. So they have becomes highly surface sensitive. So if you use them for any surface sensitive applications, so they will enhance their capacity by manifold. So this is how we have got better capacity storage mechanism in these materials. So now first I will describe a little bit about this. Like we have used oxides, nitrides, and carbon nanotubes and other based materials also for this kind of work, this supercapacitors. So first I will start with this oxide material where we have used manganese oxide, because most of the time like ruthenium oxide and MnO2 are there, and their composite materials are potential candidate for supercapacitors. But ruthenium oxide and magnesium oxide are the prominent electrode material. There are other oxide material also. This is not, but they are having much higher this capacitance, like 450 and 1270 farad per gram, respectively. Ruthenium oxide possesses very high electronic connectivity of the order of 10 to the power 4 per cm. So, however, ruthenium oxide is extremely expensive and not in much available on this earth. So, this is because of this reason. MnO2 is used because it is cheap material and environmentally friendly and present in large amount in the earth crust. So normally the MnO2 is used, but its conductivity is very poor. So normally people are doing a lot of doping and other mechanism. So rather than doing doping, what we have done, we have modified this structure. So that I will show you in by this thing, like performance of high energy density symmetric supercapacitor based on sputtered MnO2 nanorods. So what we have done, we have created nanorods of this material. So sort of like one-dimensional material we have been created for the energy storage. So this is the work we have started some long back in 2015 something. Yeah, 2000. This got published in 2016. This work. So what we do here, we take a anodized alumina template by just doing in our lab. We create a porous structure, and then we use it as a base material, electrode material for depositing thin film on. Then what we do to make it, because electrode, supercapacitor electrode should be conducting. So, but after anodization, it becomes oxides formation. So it becomes sort of like a non-conducting insulator. So to make it conducting, first we have to deposit a very thin layer of silver to make it conducting. So I will show you all those things. So then what we do, we use our sputting technique, and then we use anodized alumina template as a current collector. So for that, as I told you, we need it should be conducting. So for that, what we do, we deposit Ag silver on top of the anodized aluminum oxide. So this is the structure. So then what we do, we keep this anodized template over here, and then we deposit manganese in the presence of argon and oxygen gas in a sputting chamber. And what you are seeing here is liquid nitrogen cooled finger, copper cold finger. This is used to cool the substrate by liquid nitrogen. Why we are doing it? Because we don't want continuous two-dimensional film. What we want, as soon as the atoms from this sputter gun arrive on the surface, they should lose their energy and just get agglomerates, or they start either they form in the form of nanoparticle, or they start growing slowly like a sort of nanorod. So if you just remove also, because we have already have this anodized porous structure and this our template, so this material is going inside also. So both, and then on top of it, they are coming just like this, some sort of nanorods on top of the surface, and but they had been deep inside the porous structure also. They had gone, and then this is the kind of morphology we are achieving on the surface. So sort of nanorods. And then if you just analyze, we had analyzed it with the help of this SEM, the details. So you can see here that this is a uniform distribution is there for oxygen and manganese. This is the actual structure of manganese oxide. And then by SEM elemental mapping, you can see here, this is manganese and this color is for oxygen. So this is the uniform distribution of this oxygen or Mn particle or atoms on the overall this thing. So this is simply a mapping or by using this our SEM facility available here. So probably not many people are using this because this requires a lot of time and you should have this access to this facility freely. So that's the limit. There are some limitations for every user. So now I will just describe that this is the kind of structure has been fabricated in lab where we had what we have done. First, we take anodized alumina template, which we had made in our lab itself. Then we deposit very thin layer of silver to make it conducting. So we use anodized alumina templates as a electrode material or current collector. But because it becomes insulating because of oxide formation, it cannot act as a current collector. So to make it current collector, we have to make it conducting. So therefore, we deposit silver thin films on top of the surface. And then on top of this AG silver, we deposit the electrode material which is MnO2 nanorods on top of it. So first anodized alumina template, then silver film, and then MnO2 on top of it, and by sputtering, and then we place a Wattman paper which is doped in this 1 NO2SO4 as a this dielectric material inside them, and then we take two such samples and then club them together and form this capacitors. So there are two current collectors, this one and this one, and this is a electrode material, this one and this one, and while this middle one is a separator, which I told you is a Wattman paper for this one Na2SO4 had been used. So this is the basic structure of a supercapacitor which has been fabricated in lab, and then by having 3/4 supercapacitors in series, by just had been connected in series, and then we have tried to just charge them, and they had been discharged through a bulb over here. So if you want, I can. So again, this is the morphologically you can see here. This is the anodized annular template. Then top of it is very thin layer of silver, which is around 50 nanometer thick. This one, and this also have sort of a nanoparticle kind of thing. So on top of it, and then MnO2 nanorods. So this is the basic structure of our supercapacitor. And then these are the basic characteristic. Cyclic voltammetry measurements has been carried out. So, and then this CV curve and capacitance retention of working electrode for 3000 cycles. So this shows the stability mechanism of our fabricated supercapacitor. So this is very, very stable. There is no much deviation at all up to 3000 cycles. And these are some other parameters. So I will not go to too much of details for this because I have to cover a lot of other materials. So if you want, I can show you like maybe we can go a little fast, that how we had developed this device. This is the supercapacitor which has been fabricated in lab. Then there are 3 such devices has been taken together and joined in series. So this video has been formed. So now 3 symmetric supercapacitor devices in series. They have been joined together, all this in the series. And then you can discharge it from any, like, there is nothing kind negative, positive. So and it is direction independent. So, but you have to charge it connecting through a battery. So they had been charged through so charging of supercapacitor device using a 9-volt battery they have used for this commercial battery. So for charging, they just connecting this one lead through a battery. So in fact, battery has not been shown here. So they charge is for almost for some time, but like they had charged it for 1 milliamp or 40 minutes. After charging at 1 milliampere for 40 seconds, the device consisting of 3 supercapacitors unit area is could light emitting diode. So here is a light emitting diode. In this case, we will just after charging, we will remove this wire, then connect this through a LED. So now we will light the LED device through those. So now light has been switched off just to show this. So I will just increase it. So it goes only up to 5 minutes. After 5 minutes, it just start diminishing. So this was the very first device that has been fabricated in a lab based on this one-dimensional nanostructure materials. So now, and other kind of work, like I will show you some of the work related to this. Where we have used carbon nanotubes. So there are one student has worked related to this using carbon nanotube as a hybrid or some other form. So I will show you that what she has done. Okay. What she has done, she has made a supercapacitors using this carbon nanotube by depositing fabrication of molybdenum disulfide on top of the carbon nanotube heterostructure for symmetric supercapacitor device. So what she has made, she has like, I will just show you by step by step. First, she grow this carbon nanotube using CVD process. So by CVD process, she has deposited carbon nanotube on a using the on stainless steel by using this nickel cobalt catalyst coating by drop casting. Then put in this CVD process. Then she got this carbon nanotubes on as a substrate. Then CNT cleaned using deionized water, and then washed away the precursor salt on top of this. Then after this, she has deposited MOS2 on using this sputting technique. So I can just will share you again here that once you have this bare carbon nanotube, though you can have it by various means, but then once it forms a carbon nanotube, then it is very, very difficult to deposit anything on top of their surface because they are super hydrophobic. But so by chemical route, by dipping or doing all those things, you cannot deposit anything on top of their surface. So this is again because of the technique which I am using here is a sputting technique. So because that's an energetic process and it goes atom by atom, so they can get deposited. So at like 350 degrees centigrade, they had been kept at the heater, this carbon nanotubes, and then we had deposited MOS2 on top of this, and this comes out to be MOS2 on top of the carbon nanotube, and this gives very interesting results. So this has been basic. This is basic characteristics by structural characterization of those samples. So you can see here, these are the carbon nanotubes before depositing MOS2 on top of their surface. All this at various magnifications. But once we deposit MOS2 on top of this, so you can see here that how this MOS2 nanorods kind of things has been deposited on top of this carbon nanotubes, like some edge kind of or nanoparticle or some small nanostructures has been grown on top of the carbon nanotubes. And this is just a basic difference. And then we have used them for, because where this nanotubes are super hydrophobic, but once we deposit all these materials, this becomes super sort of like, then you can deposit material and they become super hydrophilic kind of things. So these are again the supercapacitor characteristic measurements by cyclic voltammetry. So this shows this stability and all those things. This is very good. For this is like, for example, for bare MOS2 it is here. For carbon nanotube it is here. This aerial capacitance. While for this MOS2 depositor CNT, this becomes much higher. So this is the like everywhere you can see this overall capacitance capacity will be governed by this area and closed by this loop. So this corresponds to this MOS2. So you can see that how good it is. So I will leave this and go to the next. Okay. Oh, I just wanted to show you here. All other groups also had made this kind of structure using this carbon nanotubes, but we have used here this CVD plus DC sputting technique, and we found our this cyclic stability is also remains 97% after 2500 cycles, and also their area or volumetric capacitance is very high compared to this other reported groups. And our technique is also different because there are some solution based and other things. So we have achieved much better compared to this different groups globally. And this is the basic device has been fabricated using this. Now, no, this is just another separate device, which is self-standing MOS2 on top of this CNT and MNO2 on top of CNT, one-dimensional core cell heterostructure for asymmetric supercapacitors. So this is a very interesting work. I will show you here that this has been recently published in this Carbon in 2021 only. So I will show you that what it is. First of all, we took this sample from our collaborator from Poland, who can make like self-standing sheets of carbon nanotubes. So this is the carbon nanotube sheet we took from this Gliwice University from Poland. And if you characterize them, this is the microstructure by this SEM and TM. And they already reported this work in their scientific reports in 2017. So they are routinely can produce, I have visited their lab, they can routinely produce once A4 size, this a few micron thick sheets of these carbon nanotubes, which are freestanding. So they can act as a one electrode, bare electrode itself. So by taking this sheet from that group, I use it in our lab. So this is the basic characterization. What we have done, then we have deposited one MOS2 on one. We took two samples of this. One MOS2 device deposited, and on other it was MNO2. So then it this forms sort of a heterostructure for asymmetric supercapacitor. So this is all basic characterization for that. So now you can see here, after this negative electrode characterization, like we have deposited here, tube diameter also has increased up to 200 nanometer, which is sharp distinction from bare carbon nanotubes. Here, if you just see this earlier, this bare carbon nanotube diameter is like 10 to 20 nanometer. This like here, the carbon nanometer is like 10 to 20 maximum. While after depositing these materials on top of this, the diameter becomes very large, almost more than 100 nanometer in dimensions. But you can see here the coverage which has been shown by this elemental mapping. This is a uniform coverage of these nanotubes, and the vertically oriented MOS2 flakes on top of this and carbon nanotubes are edge oriented, dominated by out of plane growth, thus providing very large number of catalytic sites for electrochemical activity. So their surface area becomes huge, which is act as a catalytic site for electrochemical activity. So that's why this capacitance becomes very large, and therefore we could publish this data in carbon. So, and also you can see here this which is the basic characteristic of a CV of a supercapacitor, that should have a sort of a square kind of a shape. So we are almost getting this similar, this square shape for this device, which has been fabricated by using this MOS2 and MnO2 on the bare standing carbon nanotubes. So this is again the basic characteristic, and then again this is for MnO2 has been deposited on top of it. So then we make it a sandwich device, and this is the voltage window for two different materials. You can see here they are working in one as a negative electrode, one is for this positive electrode. So this is the voltage window. So you can see this is a large voltage window which also contribute. And then this is the basic device formation which has been formed at CMET Pune, because we don't have this facility over here. So my student went over there and they formed this device using their facility. And then she measured after making this final device. Though this was results were not they like a very this capacitance was not very high, but the thing is there this was a unique in itself. And then in future, if you can just improve this working of this making this device formation, all those things, so we can probably improve this capacitance of these device. So now the most recent work is going on in my lab is that is related to flexible supercapacitors. One is a flexible supercapacitor, another group is working on integrated supercapacitor on a single chip. So we have got interesting results in this flexible supercapacitors. So that I will describe you here. We have used this nanostructure metal nitride thin films electrodes, again grown by the same technique is sputting, and then catalyst-free approach for fabrication of. In this case, two types of materials have been utilized. One is like cobalt nitride and zirconium nitride, asymmetric configuration for highly efficient flexible supercapacitor. And in second case, what we have done, we have used platinum enhanced capacitive performance of chromium nitride electrode toward flexible asymmetric supercapacitor, where we have used, in this case, we have used this CON and Zn3 and 2 as a two separate electrode materials, negative and positive. But in this case, we have used Cr2 and platinum enhanced Cr2n, and one other electrode material is carbon. So that I will describe you here, show you. Then why they are required? Because if you can make flexible supercapacitor, then they can be utilized for day-to-day life, activities where you are using just your energy as a heat. So they all can be utilized. And these are some. So I will just come to the directly on this. What we do here, like we deposit cobalt nitride and zinc nitride asymmetric supercapacitor by using this sputting technique. So we this can be though we deposit this in because one has to be like cobalt nitride, separate sputter source, cobalt and zinc. So it has been deposited that these are the sputting parameters for this, and this has been deposited on SS, so which is very flexible compared to this other silicon and all those things. And then this work, I can just share with you that this has been published in APL recently, last year only. So because of this only, we got very encouragement for this work, and then started some other work also to take it further. So, but before this, I will just describe the details about this. So this is the basic structure for this device. Here we have used cobalt nitride and zirconium nitride, this thing, two separate electrode materials, and then using Wattman paper as this separator, dielectric material. And then these are the different voltage windows for cobalt nitride and zinc nitride. You can see here. So this forms a large voltage window. Total voltage window is around 2 volts. So which is sort of lot very high, which is very sort of ideal. So then, if you just see here, like this CB characteristics of this device, this is at the as it is formed device without any bending. And then what we have done, we have tried to bend the device and then measure their CB characteristics. So this is it has been just bent by 40 degree, and then it has been bended further by 80 degree. So you can see here their CB characteristics, there is no much change at all in their characteristics. So they are highly flexible. So you can bend them, even then it will have the same characteristic compared to like what they have in a flat bend. And then their specific capacitance is also like it's very high current as a function of current density. So at a lower current density, the capacitance you can see here is very high, though it even at 10 milliampere also this is very reasonable. So this is the basic structure has been formed finally for this tops. This is stainless steel, and then we have deposited zinc nitride thin film electrode on this by sputting, and this is the separator. Here is Wattman filter paper soaked in a 1 m molar Na2SO4 electrolyte solution. And then again, similarly, like we have this SS substrate. On top of that, we have deposited cobalt nitride, making it thin electrode. And then we have sand divised it. And then we measured their characteristics. So you can see here this capacitance retention of this device, even after 5,000 cycles, remains very stable. So this is for the flat measurements, and this is for bend measurement almost by this 80 degree. We had been bent this device, and we see that there is no much drop in their retention capacity of a capacitance, even after there's so many these numbers. While if you just see the overall, this specific power is also much higher compared to the other reported nitride and oxide materials. So ours is here, like somewhere here, and different groups has reported, which is much lower than ours. Like you can see here, cobalt nickel, cobalt oxide, or cobalt sulfide, and all those things. So they are much lower compared to the work which has been reported from my group. And this that's why this got published in this APL. And then we have tried platinum enhanced capacitive performance of CR2N electrode towards a flexible asymmetric supercapacitor. So the advantage, we are not simply making stable supercapacitor, but we are making flexible supercapacitor, which remains stable even after bending and playing at in various geometries. So because of that, they are very, very important for this future electronic applications where we require wearable electronics and all those things. So they will be used over there. So again, using by sputting technique, what we have done. So PTCR2N, composite and carbon film electrodes were directly deposited on flexible 304 stainless steel by one step sputting technique. So I can share like here, what we have done. First, we deposit this one electrode CR2N, PTCR2N. So this chromium target and this platinum target together. So we made this composite by using this taking argon gas and nitrogen mixture. So we can form easily this CR2 chromium nitride. So it's been deposited, and then by taking another stainless steel substrate, we have deposited carbon using the same sputting technique. And then we have again sandwiched this two samples together by taking this Whiteman Na2SO4 soaked Whiteman paper as a separator, and then we characterize it. And so you can see this for both the samples, like for This is for CR2N, this is for PTCR2N. So you can see here all the peaks are available for platinum and chromium nitride, and this is for chromium nitride for CR2N, and this is okay. And then we see certain peaks of this bare SS substrate also, because this will be always dominated, that the film thickness is not very large. And then this work also has been reported in Applied Physics letter recently in 2021 only. So, and if you see their cyclic voltage characteristics, so without enhancing this their electrolytic activity using platinum, this is much smaller. And once we use platinum enhanced CR2N, so you can see here this area resembles corresponds to this PTCR2N, while this green corresponds to CR2N. So this overall areal density is much smaller compared to the this one, this red one. So this enhances the overall capacity of this capacitor. So, and then you can see the other characteristics, like as a function of bending, cyclic number and capacitance as a function of this thing. You can see there is not much change after bending this thing. And their capacitance is also very high, like 557 farad per gram at current density of milliampere, which is twofold high specific capacitance compared to pristine CR2N. So this is the advantage of this adding. So this is the basic structure of this device, where we have taken stainless steel substrates, and then then we have taken Wattman filter paper and Na2SO4 soap. So, and then we sandwich it, and then so the sum of the potential window of both the electrodes work as operational voltage window, which is 1.8 volt for PT and CR2N, because this is voltage window for this becomes 1.8 volt. And then we have measured this there. You can just see here for zero band. This is the black color shows this cyclic voltammetry characteristic, and for 80-degree band, we don't see any difference. They are completely following this earlier curve. So by bending it, it doesn't. So this is highly flexible. So the CV curve of flat and 80-degree band flexible asymmetric supercapacitor, both curve retained identical shape with same operating voltage and peak current, suggest ideal bending performance of this FASC. So these are some other characteristics for this, like as a function of different current. You can see there how this is behaving, and so this FASC shows excellent cyclability for 30,000 discharging cycles at 8 milliamp up to 8 milliampere. We have done this cycling at 8 milliampere. It retains up to 89% and 82% capacitance for flat and 80-degree band FASCs, like 92% for flat, and this 82.6% for 80-degree band at 1 milliampere. So you can just see here that how stable it is. And further, the Ragan plot also suggests that FASC attains maximum 48 watt-hour per kilogram specific energy with excellent specific power of 5.1 kilowatt per kilogram. So this is very good. Here you can just see here. And then comes now again, that is why related to nitrides. This is related to flexible supercapacitors using oxide materials. So what we have done, we have used chromium oxide and molybdenum oxide composite to make flexible electrode for asymmetric supercapacitors. So these are two different oxide materials that we utilize to fabricate again the asymmetric supercapacitors, where we have deposited this geometry using by sputting technique only. So we have taken two target materials, chromium and molybdenum. So this is the for example for molybdenum target, and this for chromium target, and we have just deposited together as this thing. in the presence of argon oxygen. So you can make separate two electrode for this. And then we have measured there. So I will show you that this is the basic characteristics of this material which has been deposited. Like for example, we have deposited Cr2O3 and molybdenum oxide. So for this is for bare substrate, this SS, and then we have deposited this red color for Cr2O3. So these peaks corresponds to Cr2O3, and this corresponds to SS again. And this is for molybdenum oxide, this the blue ones. And this red ones is for chromium oxide. So we have deposited this material. So this is the surface morphology. So we have used this as a flexible. Okay. Both sides. And this is again further. I will just skip this. So these are the electrochemical analysis of this supercapacitor, which has been formed using this Cr2O3 and Cr2O3 MOO2. So these are two separate this electrode materials. So the charging curve are highly symmetric and linear. Here you can just see here for this Cr2O3, and while for Cr2O and MOO2, so you can see here this becomes much higher, this overall area. So that shows this capacitance increases. It also suggests that the Cr2MO2 composite has good reversibility in comparison to original Cr2O3 electrodes. The specific capacitance of pure Cr2O3 and Cr2O3MO2 composite thin film was found to be 273 farad per gram and 340 farad per gram. So you can just see the difference here, and at a current density of 2 milliampere per centimeter square. And then, okay. So, and this work has been reported in Applied Surface Science recently. And then these are the different bending tests for the same device. So you can see here, the based on operational window Cr2O3, this composite thin film based electrode was taken as positive electrode, and carbon based thin film electrode was taken as a negative electrode. So the separate Whiteman paper, one Na2SO4 was used. So then you can see that all the CV curves are identical in shape and retains almost same voltage window with same peak current here. You can see here, this current is almost same for all this measurement at different bending, like 0 degree, 80, 40 degree, 80 degree. They are all same. There is no much difference. So that confirms the performance of device is ideal at various bending angles. So this is highly flexible. And this is here, it is how it shows this voltage windows. It can overall it becomes 1.9 volt, so which is very ideal for this work. So the specific capacitance of carbon thin film was found to be this much. So I will just skip this. And these are the like their stability measurements, like up to 2000 cycles, there you don't see much change, and this also remains the same, 91%, and like and 86% for the bending at some 80, 80 degree or something like. So device shows cyclic retention of 91% for flat and 86% for 80 degree band. The device at 20,000 discharge cycles. So these are 20,000, not 2,000. That indicate long-term good cyclic stability of the fabricated flexible asymmetric supercapacitor device. So this is the kind of work has been reported from my lab. So this also has been published in this thing. And then finally, these supercapacitors may be used where high power or energy storage required. Then supercapacitor can be used widely because of their long life and short discharge time. Further research is needed in the enhancement of energy density and lowering the cost of supercapacitor for them to compete with the storage technologies. So I just, and these are some of the which has work which has been carried out from my group. And then these are my project, which I had completed at IIT Roorkee. And these are two projects which are going on right now. Actually, I have got a very challenging this project, like this one, fabrication of high energy density thin film based on chip supercapacitor devices using sputting technique. So this is currently the work going on this device to fabricate this. And these are my consultancy projects, and these are now the some 26 PhD has been awarded, and 15 students are in progress. And this is old slide, so the publications has gone up 2020 more than 20 degree 20 or more. And thank you. So now I will be happy to take some questions from the audience if they are available.
Yeah, thank you, Professor Chandra, for excellent talk. Nipun, can you take questions from the chat box?
Yes,
Or
sir. Thank
audience, if someone.
yes, yes.
Yes.
Thank you, sir, for such a nice talk. We have a first question from Mr. Surendra. He's asking, can the supercapacitor be used for laptop or mobile battery? Because as supercapacitor has high power density, means it can quickly charge and discharge. So if we want supercapacitor to stay charged for longer duration, in that case, how it is relevant?
First of all, because actually right now also they are being used in all the devices, whether it's even your phone or this laptop, and everywhere they are being utilized, because there are certain cases like when there is a certain power failure by chance, by any other fault, then initially they can just take care immediately, like a supercapacitor can deliver very high power immediately, but which is not feasible with the battery. So they are already being in use in all these electronic devices, but certainly they cannot be used for longer duration because they don't have that kind of storage right now. So in that direction, the research is going on day by day to enhance their higher energy density. But they are being used already in these devices and will be used in future also.
Okay, thank you, sir. We have another question from Mr. Rajat. He's asking why specific power of electrostatic capacitor is higher than supercapacitor as shown in your slide.
Because this is electrostatic charge which resides on this surface of this your electrode materials. You take like two simple plates are taken, while in case of supercapacitors, this structure is entirely different compared to a simple plain conventional capacitor. So the structure is different, and because of that only this specific power is less compared to that conventional capacitor, because of their structure.
Okay, thank you, sir. Another question he is asking, like Professor, as you said, supercapacitor value goes up to 150 farad. How it is possible to store? How it is possible to store that much of charge in small area? What is the basic principle behind it?
Because the surface area has been enhanced by manipulating the structure of these materials only. So that is the basic research which is going on, which I am showing you that how we can manipulate this area. Like I showed you that by just taking 1 centimeter by 1 centimeter area of a silicon substrate, I can make it, rather than 1 centimeter square, I can make it almost within the same volume, 1 meter square, the same thing. So that's how we store that large charge on that surface, because of by enhancing the surface area. Because I have not changed the silicon substrate volume, that is 1 centimeter by 1 centimeter again. But the only thing is that by just making it porous structure, I have surface area, and which all these supercapacitors, they are surface sensitive. The charge remains on the surface. That's you can enhance that much of charge.
Okay,
Up to
thank you,
like
sir.
capacitance.
Yes, sir. Another question he is asking, like, are these nanorods morphology in your sample possible by any other synthesis process except sputtering? which can also be effective against hydrophobic nature of substrate.
Yeah, different groups has made this kind of morphology by different techniques. So this is not limited to only sputtering only. So this is feasible.
Okay, I hope he's clear with his questions. Another question is from Mr. Sumit. He's asking, in most of the research papers, I have seen that galvanostatic charge discharge measurements are performed in the positive potential range, starting from 0 volt, through the CV measurements are performed from a. So actually, he's not completed his question. I think we may move
Probably
to next question.
I may not be. Okay. You can take the
Yes,
next.
sir. Yes, sir. Yes, sir. We can take the next question. It's from Dr. Debanjan. He is asking, what is the energy density of developed supercapacitor? Is there any comparative study? What are the strategies to increase the same?
Already this energy density has been day by day they are being enhanced, but not up to the like energy density of batteries. So they are much lower compared to batteries. Their power density is higher, not energy density. So this is the major drawback of the supercapacitor. So they are being enhanced.
Okay. Then we have another question from Mitri. He's asking, sir, can you suggest some more materials which can be probed in the area of supercapacitors?
Because what recently we have worked on, they are very new materials only. They have been reported in the recent literature. So similar to that, you can try other materials also which are cheap and easily available in the market compared to like some of the materials are like platinum is very expensive. So by replacing some other catalytic materials, we can try some other materials also. I cannot predict what material will be better unless we try it, use it.
Thank you, sir. We have another question from Mr. Srinivas Yadav. He's asking, sir, can you please suggest how to improve adhesion between graphene-based thin film and substrate to control peeling of film during charge-discharge cycles, analysis during CV measurements?
Actually, this again depends upon what process has been followed to deposit this thin film on the substrate. Because in our case also, we also face this kind of problem like peeling off. So to avoid that, we normally deposit very thin layer of chromium to make as a base layer. So that improved a lot. But again, because most of these work is not being carried out using sputting, this is being carried out by chemical route, so I cannot comment on that. What material they can use to stabilize on the substrate surface stability.
Thank you, sir. We have another question that has just come up from Mr. Surendra. He's asking how the chromium oxide is helpful for better supercapacitor performance. Another thing is that chromium oxide is carcinogenic in nature, so how it can be applied for real-time applications?
First of all, the kind of material which is used in thin film pod, which is very small. Okay. But again, because of their large voltage window and all those things, they are utilized. They are good material for developing this kind of devices. So here, whatever material we are using, this is in a very minute quantity. This is not very large quantity. So this will not be that harmful compared to the bulk supercapacitors.
Okay, thank you, sir. Amit is asking what could be the possible reason behind the charge-discharge curve saturation at low current density after some cycles in supercapacitor device?
Because the area is limited, and once they completely gets charged up, this whole area is covered. Then there is no further chance to accumulate the more charges on that, because it will start repelling.
Right, sir.
So this is this area dependent only. Up to a certain limit only you can accommodate the charge particles, charge.
Okay. Mr. Sumit has cleared his question now. He's asking, In most of the research papers, I have seen that galvanostatic charge discharge measurements are performed in a positive potential range starting from 0 volt. Through the CV measurements, though the CV measurements are performed from a negative to positive potential range, why is it so?
Because we have to, because there is a cyclic voltammetry. This is we have to completely cover this whole voltage from negative to positive. So we are having one is a cathode and another is a anode material, which we are taking. This we are working in different. Probably I may not be very clear about this, what he's asking and what I'm explaining. So probably because I have not done these all experiment myself, my students used to do it. So I cannot comment much on about this problem.
Okay, no problem. So thank you. I guess with this, we are done from questions in the chat section. Yes, sir. Rajat wants to ask something. Let me just unmute him. Hello, Rajat. Can you hear me?
Am I audible, sir?
Hello. Yes.
Yes.
Please go ahead.
Okay. So good afternoon, Professor, sir. Re-emphasize
Yes.
the
Good
point,
afternoon.
yes, sir. So as I asked about the 150 farad capacitance value, or about the supercapacitor, sir,
Yeah.
I mean to ask is like, if we think about like literature reviews, capacitance of Earth is about in millifarad. So I meant to ask is, how is this possible? Like in supercapacitor, we goes up to 100 of farad and 150 of farad. So how is it
Yeah.
possible? How you are working in it?
I can compare with one example. Just I think that will make it much more simpler for you, Rajat. Like what is the magnetic field of Earth? Are you aware of it? Hello?
Yes, sir. Yes, sir. I think it is of the order of milli, maybe 10⁻².
Milligauss.
Yeah.
Yeah, 3 milligauss, 300
Yes.
milligauss or something like that. Isn't it?
Yes, sir.
And while we can generate magnetic field making superconducting magnets in lab up to 14 Tesla, 20 Tesla, or up to 40 Tesla. So this is same thing. So what you are talking about is Earth's capacitance. What we are doing, we are deliberately creating this within a surface, within a very small area, by modifying or manipulating the surface structure of those materials. So there are there is nothing, there is no comparison of like this, like Earth is limited to this 300 or 400 this millifarad or something like that. So it is similar to that. I hope it is clear to you.
I will go through with the literature. So I think it will be fine for me. Thank you, sir.
Okay.
I think, sir, we are done with questions. I once again request from the audience, if we still have time, if anybody wants to ask something, Professor, you can just raise their hand. No. Okay, so may I request Professor Mahesh, sir, to kindly proceed.
Yeah, let me thank Professor Ramesh Chandra for accepting our invitation and delivering this excellent talk. And
It's my honor.
yeah, participants, they have benefited from your both talks. So thank you very much.
Okay. So it's my honor, Mahesh. Thank you very much for inviting us. Okay. Good.
Yeah, thank you so much. So with this, we close the session, and yeah, next talk will start at 2 p.m. So in the afternoon, we have both talks on first talk is on the biosensor, and then we have the hydrogen sensor, because yesterday someone has asked about the questions about the hydrogen sensor. So second talk is on the hydrogen sensor. Yeah, thank you very much. Yeah, thank you, Professor Chandra.
So I can leave now.
Yes.
Okay.
Thank you.
Thank you, sir.
Yeah, thank you, Dipul. Yeah, hi, good afternoon, Dr. Sakshi.
Good afternoon, Dr. Mahesh.
Yeah.
Am
So,
I clearly audible?
yes, you are audible. So, Nipun, are you there?
Yes, sir. Good afternoon, sir.
Yeah, good afternoon.
Good afternoon, ma'am.
Good afternoon, Nipun.
So, we can start, Nipun?
Yes, sir, sure.
Yeah.
May I request ma'am to kindly share her screen?
Yeah.
Sir, your mic is mute. Please.
Yeah, Nipun, yeah. Yeah, slides are visible.
So, shall we start, sir?
Yes, Nipun.
A very good afternoon. I am Nipun Sharma, student host for this event. Welcome all panelists and our dear participants again in the afternoon session of the AICT Training and Learning Academy sponsored 5 days online workshop on nanosensors. In the morning session, we had really nice talks from Dr. Jitendra Singh from CD Planning and Professor Ramesh Chandra from IIT Roorkee, who gave us the invaluable insights of their research work. Moving on, so I would now like to welcome and introduce our next speaker to the audience, Professor Sakshi Danekar, by sharing a brief biography about her. Dr. Sakshi is currently working as assistant professor at Department of Electrical Engineering, IIT Jodhpur. Prior to this, she had worked as a sub research scientist and inspired faculty at Center for Biomedical Engineering and Center for Applied Research in Electronics, IIT Delhi, and as an assistant professor at MIT Institute of Technology, Noida, from 2011 to 2012. Her current research includes from the fabrication to prototype development of sensors for social causes, microfabrication, nanomaterials, MEMS, and semiconductor devices. She is on editorial board of the IEEE Sensor Letters, senior member IEEE, and IEEE ambassador, and young professional chair of the IEEE Sensors Council from 2019 till present. She is chairing an IEEE Sensors chapter jointly with Delhi and Rajasthan. She has more than 40 research papers, few Indian and US patents filed, and one patent to her credit. One of her projects funded by BIRAC is for developing indigenous alcohol breath analyzer, and she hopes to convert this into a startup. She has been awarded with IEEE Young Professional Hall of Fame Award in 2019 in Montreal, and her team was awarded first position in the North Zone in the Tata Hackathon Tata Services Limited in 2017. So with this brief introduction, may I request Professor Sakshi Danekar ma'am to kindly deliver her lecture for us. Please ma'am, so over to you now. Ma'am, I request you to kindly unmute you.
Yeah, please unmute.
Sorry. Sorry.
Yeah.
Yes, ma'am.
Somehow I was not able to see the unmute option. Okay, yeah, it's fine now. Yeah.
Thank you.
Thank you, Nipun. Yeah, thanks for the introduction. So, thank you, Dr. Mahesh, for inviting me for this lecture. So, I will talk about MEMS and microfluidics for bio applications. So, it's important to first understand that why we want to talk about MEMS and microfluidics, right? So, I will start with a very basic introduction. I will also talk about some bio applications, biosensors. Just give me a minute. I'll just scroll to the next. Yeah. So this is the outline of my presentation. So first we'll talk about why do we need these MEMS and microfabricated devices, right? And then why silicon? we know that there are lots of materials that are being explored in the current time. So, but even then, silicon is something which is conventional, but is still being used, right? So we'll talk about silicon, why it's so special. Then we'll cover up some biosensors and biochips, right? Then MEMS, microfluidics, and then I will talk about some processes. Let's see how time goes. If we have time, I'll talk about it in detail, or else we'll have just a surface level introduction. And in the end, I'll show you some microfluidic chips that I have developed when I was working at IIT Delhi. So coming on to the first one, what is microfabrication? So I don't know how many of you know about it, but all these MEMS-based devices, MEMS means when I say micro electromechanical systems, right? So these are developed using standard silicon processing techniques, right? Which is conventional and very well known. So how they are made? They are made by these microfabrication, right? So that means we are developing structures which are more at the micron level, right? Where we talk about the range in micrometer, 1 micron to 300 or 300 micron to 3 mm, or 10 nanometer to around 1 micron is where it moves on to nano electromechanical systems. Right. So I'll show you some more devices and I'll also explain as to how these work. But all these are made using these standard processes of microfabrication. So you can see on the right hand side, there are some chips that I developed when I was at IIT Delhi, and these are some MEMS based switches, right? So this is after packaging and this is before packaging. So how they are made, what processes they use, that I'll come in detail with. Okay, so coming on to silicon, right? We talked about micro electromechanical systems and how they are made on silicon wafer, right? So the thing is that silicon is very old material, right? It is very well known, very well explored. All the processes are set, right? Now, there are some more materials that people are working on, which are not so traditional, and they have their own advantages, right? But all these ICs that you see on the back panel of your CPU, or if you see in your laptop, even till today, they are all being made in silicon material, right? So silicon is the material for past, present, and future. Now, why it's so special, right? One, it is very easily available. You know that it is found in the form of sand, right? And then you can modify it easily. So suppose I want a chip made on silicon wafer for application A, then I can use it for application B by modifying the surface, right? The processing is much cheaper. So when I talk about processing of, say, these all silicon wafers in one go, this is a one cassette of silicon wafers, right? So when we talk about a processing of all of these in one go, then it becomes much cheaper. Then it can be easily doped. We know, we all study about P-type silicon, N-type silicon, right? Extrinsic silicon. So it's easy to dope these this semiconductor, which is silicon, right? And best part about it is durable and stable. So a lot of devices that are being made on silicon, one, they are made with standard processes, and second, they are durable and stable, right? Then it is present in ultra pure form of single crystal. So only those participants who have actually worked in the area of silicon or are presently working in the area of silicon will understand the meaning of why we want to work in single crystal, right? So that will be like little later. So as of now, it's just like a good to know information. Then it is present in different forms, right? Polysilicon is one of them. And years back, a research started where polysilicon was also used as your gate electrode in a transistor. So polysilicon has properties that it can even replace metals, right? And so is silicon a workhorse of microelectronics and MEMS. Okay, so this is the Czochralski method. I'm sure many of you know about it, how silicon wafers are made from sand and prepared in this form of an ingot, right? And then they dice it and make it into thin discs, which I showed here, this one. And then you get this one silicon wafer. So this is just a process. It's a standard method. I think probably I can skip it. And this is more about the crystal structure of silicon, how many electrons it has. So we know that silicon is a semiconductor material, right? And in fact, if you are working in the area of sensors, there are lots of materials which are not silicon, but also they are used because they have semiconductor properties. So that's the best thing about this material, that this is like an ideal material that you can dope and change its conductivity, right? You can make it nanostructure, and then you will see an entirely different range of applications where you can use this material. So now identification of silicon wafer. So if you buy silicon wafers, right? So even before you buy, you have to know what you want to do with the wafer, right? Every kind of wafer has its own way of being processed. By this, I mean that whether you want N-type or whether you want P-type, or what kind of orientation you're looking for, right? Suppose I want to process this kind of wafer with process A and process B. So I have to know beforehand what kind of silicon wafer I want, whether I want N-type 100 or P-type 100 or N-type 111, right? So one easy option to identify a wafer by looking at it and know its type of dopant and orientation is through the flats. So these are like standard markings that a company will provide on the silicon wafer when they are manufacturing it, right? So it is, by looking at it, if you see two primary, these two flats opposite to each other, you know it's N-type 100, right? And of course, there are ways to characterize it also, but this is just for a quick identification. So one thing that you're required to know when you're working in the area of MEMS or microfluidics or silicon wafer processing is starting wafer, right? What it should be. So you should know all the details, right? Even the thickness. Okay. So coming on to biosensors and biochips. So what are these biosensors? So we know that these are the devices whose property will change when they interact with any kind of biomolecules, right? And so we call it as biosensor, right? Sensor is something whose properties get manipulated. And here it's biosensor because it is being exposed to some biomolecules, right? And where we talk about biochips are mainly those platforms where you have sensor and other electronic circuitry also together on the same platform, right? That's more like a system, and this is more like only a device, right? So when you work in the area of biosensor, something that one needs to understand is that which property are we looking at? Are we looking at any electrical change or mechanical change, some other physical change or optical change, right? And that will define the focus area of biosensor, right? Suppose I talk of a sensor where when it is exposed to, say, coronavirus, we see a change in, say resistance. So that means its resistive property is changing, and so it becomes electrical. And say I talk about a device which, when exposed to coronavirus, shows a change in movement, say up and down, and there it becomes like a mechanical sensor, right? Any device that is exposed to, say, virus and shows a change in light, right? That becomes an optical sensor. So it is important to know as to which exact area you're working upon or what you want to work on. So when you actually read papers about biosensors, you will find lots and lots of information, right? Slowly you narrow down to see which exactly the mechanism that you want to work on, right? So how does this system work? This is the picture here in yellow that you see is more to do with the system, right? You have a sample, you have water, food, air, right? This sample means any kind of bioanalyte, right? Which has say bacteria that you're sensing or something else, right? So one important thing that you need to do is separation. So suppose you have bacteria and water. One is that your sensor is so capable that without even separating bacteria, I put some drops of water and it's able to catch it, right? And if the system is not such, what you can do is you can do a kind of separation where your bacteria is, say, kind of segregated from your main sample, from water. So it's more of concentrated bacteria that you have. And then you do the detection, say, based on antigen, antibody, or DNA, right? And then you do data analysis, and this comes a more of analytical part. Right, so this becomes your complete biosensor system. Like when we see our glucometer that we use at home, it's more of a system, right? Inside there is a device, which is a sensor, right? So it's a biosensing system. Okay. So these are some of the applications of where biochips are used, right? So if I say biochips, I'm talking about more of a system, but even biosensors for that matter are used in all of these areas. And in addition to this, there are many more applications, right? What is most important thing that is needed for any biosensor or biochip, right? One, you want it to be sensitive. If I want to detect bacteria, I want the bacteria to be detected at, say, a smaller quantity, right? Then it should be quick. Now, suppose we come up with a device which can detect if the person is COVID positive or not. So not that you have a kit at home and you use it today and tomorrow it tells you, right? We want everything in 5 minutes. 5 minutes is also longer. Actually, people want it instantaneously, right? So it should be rapid, and then it should be low in cost. It is important that the sensor that you're working on is affordable, right? And there are some companies which have actually commercialized these biosensors. These are some of the names, but there are many more. And on the right-hand side, you can see the kind of devices they make. You can see how small it is. It's almost the size of a coin, right? So this is what is needed in today's time, something which is portable, something sensitive, rapid, affordable, right? So that you don't waste a lot of time in going to the lab and then getting the data and then processing it, right? And with the need of this miniaturization came up something like MEMS, NEMS, even microfluidics, right? I'll show you how these systems work. So these are different methods by which, all these microorganisms and cells are studied, right? So it is showing that there is an inlet and there is an outlet, and these are different kind of systems. So it's not that all of them use these, right? One might use dielectrophoresis, the other might use antibody based capture, right? Some other system might use impedance spectroscopy. So each method has its own unique way of separating out your bioanalyte and then showing the detection, right? So like in the end, you can see these are cantilevers. Cantilevers are MEMS-based devices, and then nano FETs, right? So see, it is also important to know what size of molecule you're detecting, right? Like bacteria is much bigger than virus. So it is possible that out of these one method, detection of bacteria is the best, but may not be applicable for smaller biomolecules like virus. And for that, then you need some other method. So when you work in the area of biosensors, it's important to know what size of bioanalyte you're detecting. It is in which medium? Is it in air? Is it in water? Is it in body? Is it in a cell? Right? And then what detection mechanism you want to use. And once all that is clear, it is important to know what kind of material I want to use, right? What kind of processes will be used. So basically this outline is to be framed before you actually start working on biosensors. Okay, so coming on to MEMS devices, what I just told you the full name of it, which is microelectromechanical system, right? But mainly it's a combination of mechanical and electrical components together on the same chip. So suppose if you see this picture, right? So this is like a cantilever, right? It can go up and it can go down if, say, I apply a voltage, right? So suppose I want to send a signal from this terminal to this terminal. I mean, this terminal to, say, this track, which is another terminal. So if by some mechanism I can put this cantilever down, the signal which was here gets in touch with these electrodes and gets passed on, right? So it's possible to say pass the signal from one electrode to another when they are in contact. So this becomes like a switch, right? And this gray, light gray thing that you see is entirely made in silicon. At the bottom that you see is also silicon, right? So it's almost like creating tracks in the wafer, right? So working in the area of MEMS is almost like one has to be thorough with the microfabrication techniques, right? Microfabrication processes, right? Be confident with all the processes, and if needed, be prepared for repeating the entire process. I'll show you one process and explain what I mean by this one, right? So it is combination of mechanical functions where we are talking about sensing, moving, heating, right? And electrical functions, which is to do with switching or voltage, right? And everything is being done on the same chip. And you can see here that how tiny these sizes are, right? So each of them has one application. So one of the most commonly used MEMS devices that we hear is gyroscopes, right? Accelerometers. You use them in your car. You use them even in your phone, right? Gyroscopes you use in your phone. So in today's time, MEMS is something which is also well known. The challenge with MEMS is its fabrication, right? It's design principle, how you design it. And after you design it, how do you make it possible? So you have to make this thin layer of silicon go up and down. And then when you say that this is a ready device, you also have to inform as to how many times it can go up and down, how many times it has been tested. If you say 5, then it's of no use, right? So it has to be a lot of trials given to a MEMS device before we say it's ready for the application. Okay, so coming on to accepted size range for MEMS, right? So we have this is the nanometer range, which is like more towards the nanotechnology side. And here where we are talking about MEMS is the microsystems, right? So they generally have the size range, the dimensions are somewhere between 1 to 100 micron, right? Okay, so coming on to BioMEMS, right? So we talked about some biosensors, some biochips, and then MEMS. Now, if I club them together, that means I talk about MEMS-based devices, which means that devices which have the property of, so, say, mechanical motion, right? Or change in electrical property upon application of a bioanalyte is somewhere we are talking about BioMEMS, right? So BioMEMS itself has a wide range of application. So you might have heard of these micro needles, right? That nowadays people say that there are injections that you can get, but you will not get hurt, right? So these are all I should say the more exploratory part of BioMEMS, right? Painless needles. then organ on a chip or microfluidic cell culture, right? These are all also falling in the category of BioMEMS. Even some of, actually, if you see point of care diagnostic chips are a lot dependent on microfluidics. And at some point, they also club microfluidic with MEMS, right, to make these diagnostic devices. So once I cover up microfluidics, then I can explain why this combination can be very attractive, right? And then, of course, miniaturization is something that MEMS is needed for, right? You make microsystems using your microfabrication processes. Okay, so this we have mainly talked about different scales and sizes and where is microelectronics and MEMS lying, right? And then you further go down to the nanometer size is where nano scale functional elements are found, right? So I don't know how many of you know about this bottom-up approach and top-down approach, right? So bottom-up is mainly talking about things we build from the bottom. Right? From nanometer, say we grow something and make it into, say, 100 nanometer size. This is one approach. The other becomes top down. So I have something big at the top and we break it down. Right? So mainly like in MEMS structures where you have, say, some kind of etching done, right? You remove some part of the substrate. If you see this one, right? Where you are removing, you're creating this track. Before processing this whole thing would be light gray. So I make this track, then I make this hole, right? And then we cut this part out, then we remove this part out. That means this whole substrate was available and now we are cutting it down from different sections. And so we are following top-down approach. Right? Okay, so important aspects for fabrication of BioMEMS. Materials is something extremely important. One has to know if it's silicon, then what type of silicon that I've already discussed. And now people are also exploring flexible materials where they talk about polymers, right? What kind of polymer you can use to make similar track that say I can make in silicon. Say I make a track in silicon, which is say 100 micron wide, right? So then they are also, the scientists and researchers are exploring other materials where I can get 100 micron wide channel or a track, right? Without going through the entire silicon processing. So that makes life much easier if we go through these polymer-based devices, right? So every material has its own advantage and disadvantage. It entirely depends on the key application and the expert who is working on that device, right? Then SU8 is another material that people use to make your MEMS devices, right? Glass and quartz are also used. Sometimes they are also used for some kind of packaging, or they are used for making these devices, right? And also now coming towards organic devices, people are moving towards biological materials also, where they're trying to use, say, some proteins for some kind of, say, a positive charge or a negative charge on the device, right? Then the other important aspect for fabrication of BioMEMS is fabrication processes, right? Wet process or dry process. So one has to know if it is a wet process, like I showed you in the beginning, the choice of silicon wafer is dependent on what process I'm using, whether to go with a wet or a dry. It is possible that one kind of wafer will go through wet but may not go through dry, or may go through dry but may not go through wet, because the way they work are quite different, right? Their basic working principle is quite different, right? Then one has to understand the surface chemistry. So when you're working in, say, bio application, and suppose you want to detect say COVID, right? Coronavirus. Then you have to know how it will attach to the surface. So the surface chemistry becomes extremely important in case of biosensors or biomems or biochips, right? Whether I put blood on it or whether I put water on it on the device, right? Whether it is hydrophobic or hydrophilic, the surface. This is important to know. So surface chemistry needs to be known in detail. Then it is important to know the nature of bioanalyte, right? What kind of chemical nature or physical bonds it has on the surface. So basically it's attachment of this bioanalyte on the surface. So the chemistry of both should be well known. Then is robustness, right? So if I make a device work in Jodhpur, right? Say in 42 degrees centigrade, and then I take that device to say Kashmir, right? Or Ladakh, where the temperature has dropped down considerably. So will the device work the same way as it was working in a hot temperature? Right? That needs to be explored, especially in biomems or biosensors mainly, because you're working with bioanalytes and they are very sensitive. These cells, proteins, DNA are very, very sensitive to temperature. Right? When you do lab tests, they are more in controlled environment. But when you take it to the actual place where the testing needs to be done, they might behave differently. So this all needs to be explored before finalizing the results of your device, right? And then conditions for testing environment. So if you have seen some of the data sheets of sensors, they always mention this will operate best in this to this humidity or this to this temperature, right? So this needs to be known before you work on any application of biosensor. Okay, so how is cantilever a biosensor, right? So we have talked about some MEMS devices, how MEMS devices work and in what range they are made, right? And I also explained that initially when you take silicon, it's all gray, right? Now imagine that this is say a cuboid, right? And I remove some part of it and leave this much of structure hanging, right? Now, whether its dimension is in micron or not, dependent on that, it can behave like a MEMS device. So this is just for imagination that there is a cuboid and we cut out some part of it and just let the hanging structure be, which behaves like a cantilever. And cantilever is something which is a MEMS-based device. So let's see that how will a sensor behave like a biosensor when it's a cantilever. So when the cantilever, say the hanging structure is not moving, right? And then I add some bioanalytes and it starts to bend, is where we say that it is sensitive to the weight of these bioanalytes. Right? Now let's see how this weight can bring in specificity. So suppose this is my cantilever, right? And here I have, say, chrome gold. So this is just a cross-sectional view, right? And then we add some receptor molecules at the top, right? These receptor molecules, which are these antibodies, are specific to my antigen, right? So as these antigens, because they are in a lock and key mechanism with this antibody, will come and get attached to them. And as they keep attaching, the cantilever will bend. Now, depending on how it bends from X to X1, right? How much deflection has happened is something that will tell you how sensitive it is, right? So this is more to do with this target getting bound to these green antibodies. Now, suppose they are of some other nature. Say these are not the antigen for these antibodies. It is some star shape. Then they may not fit here. If they will not fit here, this cantilever will not bend till X1. It might be somewhere closer to X only and may not show any deflection. And that is how a MEMS-based or cantilever-based sensor works. Right? So suppose I have two cantilevers, right? And I have put two different antibodies. One is in yellow and one is in blue, right? And these blue and green are, say, in lock and key mechanism. But these green and yellow are not in lock and key mechanism. So what will happen that when you place your antibodies, these cantilevers will slightly bend, but they will remain in that reference position till your antigen arrives. So here in blue and green, it's like a specific antigen for this antibody and make this cantilever bend. Whereas on this cantilever, where you have yellow antibody, it is not bending at all because this green antigen is not specific to the yellow antibody. Right? And that's how we can say that this is more sensitive than this. Okay. So this is more theoretical. Okay, so coming on to microfluidics. Right? What is fluidics mainly? Fluidics is nothing but flow of your liquid and gases and how you study this flow of liquid and gases. Right? Coming on to microfluidics. Now we are talking about flow of liquid and gases in small volumes, right? In microchannels. That means we create tracks which are really small in the size of micro range, right? Now, how a liquid flows through a bigger pipe or it flows through a microchannel is a totally different mechanics, right? Why I'm saying mechanics is because this is more to do with fluid flow, right? So microfluidics is more to do with some part of mechanical engineering and some kind of biosciences. Yeah. So okay, so why do we need microfluidics? Why did the need arise at all? Right? When we're talking about biosensors, we are talking about many genes and many proteins in the human body, right? And every gene and this proteins are very unique, right? If we talk about their properties, they have something unique to themselves, right? And that's how it becomes more complex. And that's how we hear about this COVID nowadays, that the virus enters the body, but it behaves differently in different people, right? Because our body types are all different. And that's how the complexity arises. And if we talk about big volume liquids, so say, give me a second, I'll just change it to a pen. Okay. So if I talk about, say, a big container, right? And here I put lots of liquid, right? And then I talk about, say, just this micron channel where this liquid will flow, right? So here I will need some ml of liquid, and here I will need, say, some microliter of liquid, right? So in microliter, you will need 10 microliter, 2 microliter of liquid, right? And in ml, you will need many microliters, right? This goes up by a factor of 1,000, right? So suppose I'm working on, say, virus, right? Coronavirus. I'm talking about coronavirus because it's very relevant in today's time. So suppose I'm working on virus and, say, some antibodies, right? So even these few microliters of antibodies would cost me some couple of thousands. And if I want some ml of antibodies, probably couple of lakhs, right? So why not work in smaller volume, right, in lesser cost and get, say, a more precise result, because with bigger volumes, the precision becomes challenging. Right? And that's how from the traditional instruments that we had, where people were working in ML mainly, thought that it will be useful to have really tiny reservoirs or channels through which the same liquid can pass through and give us the same result as we expect from ML beakers. Right? So that is how the solution came as microfluidics. So these are small fluid quantities. It gives high throughput and it's faster. Faster in the sense that you only work at the dot. Dot means suppose it's 16 channel, right? So I put the liquid here and it passes on and then I get the result here, right? Now in comparison to this, if I have to take 50 ml of one and 50 ml of other liquid and then say mix them together and see a reaction, that might require more resources and more volumes. Right? And it might not be as fast as this is. So the main advantage of microfluidics is reduction in size. Right? The only thing that is required to be studied when you're working microfluidics is when the liquid is or the gas is flowing through this tiny channel, if the flow is smooth enough, right? If it is moving with noise or without noise or less noise. Right? How is the surface? So when say anybody is walking on a track, whether the track is smooth or rough, whether there is more friction or less friction, all that needs to be studied when you're working in the area of microfluidics. Right? What is the speed of it? So suppose I want a response in 2 minutes, right? And suppose these two liquids which I'm trying to mix give me the response in say 10 minutes. Then it may not be useful for me. I have to find a way out so that they can quickly get mixed or react and give me the response. Right? Then one other advantage that microfluidic gives is multi-agent detection capability. So you can have something like 1 inlet, 2 inlet, 3 inlet, and you can connect them with, say, one channel here, right? And say get an output here. So I can have multiple targets, right? Whether it gets mixed, whether it gets react, or even if it does not react, suppose I have something at the base and I pour something from the top, right? And then they get mixed up and travel through the channel and give me the output. And later I want to mix this response with these two as well. So I can have multiple ports. So I can design microfluidic channel as per my own need. Right? There is no mandate. There is nothing like only this needs to be done. So if you actually work in the area of microfluidics, you will see that there are various ways of designing it. Right? And the interesting part is that microfluidics is actually not new. So you have our human body, right, has a lot of microfluidic system in us. All the arteries and veins, capillaries and plants, right? Everything is of almost the same dimension. So it basically needs to be explored, right? It's nothing like an invention. Invention will be when you do it in a new material, in a new way. Okay, so these are some of the examples where, so say I have to test one liquid, right? And I just want to put a drop here and I want to check it at every port. So I can make a microfluidic channel with different fingers. So suppose I need 3, then I make only 3 fingers, rest I don't make. Or if I need many, then I can make it pass through all of these and then do the testing at this port, then at testing at this port, and then testing at this port, so on and so forth. Right? So other thing that one needs to know is if you're making it pass through a narrow channel or a wide channel, and how much wide you need. So suppose you're talking about some really viscous liquid, right? Thick one. then you may not be able to pass it through 10 micron wide channel. You might need 200 micron. So that depends on your application, what you're working on, what liquid will flow through, whether it is gas or whether it is liquid, what is the viscosity. Everything needs to be known before you design a microfluidic channel. Okay, so before I move on to the microfabrication processes, I would just like to give one simple example as to suppose I have, say, a MEMS, say, device where I see, say, I have a piezoresistive material, right? So I'm seeing some change in resistance, right? So suppose I have a material here, which is piezoresistive, right? And I will see a change in resistance when I put, say, few drops of an analyte, right? And this will only, say, this only requires, say, few, say, microliters, right, of liquid. So what I will do, then I will make, say, a microfluidic channel, depending on the design, how I have, what I have, how many fingers I need, or if I don't need fingers at all, right, just an input and output. And then this can be connected onto my MEMS device, and there I can see a change in sensitivity of MEMS device after the liquid has flown through the microfluidic channel. So this is how you can do some kind of clubbing if needed. Right? But clubbing is not mandatory. These are just the options. Right? Okay. So coming on to microfabrication processes for MEMS, microfluidics, or any kind of a microfabricated device. So these are some of them, right? There are still more processes that are used in fabrication processes, right? The most important one starts from silicon polishing and cleaning, right? So, okay, so I will just brief you on these. I actually did not plan to show you in detail because then it becomes a really long lecture. So when we talk about cleaning silicon wafer, right? Actually, any substrate that you use, whether you use a flexible substrate, a glass substrate, or you use, say, say polymer glass, Corning glass, right? Silicon wafer. The one important thing that you need for any kind of substrate is it should be clean, right? It should be dirt free, so that when you are working on micron level, working at micron level or even nano level, you should not see dust particles, right? Or any unwanted particles on the surface, right? So it is extremely important to have a clean substrate before you start working on your devices. Now with silicon, there is a standard known process for cleaning, right? And every step has its own process. When you're removing and say any contamination at every level, it has its own way of getting removed, right? So this becomes the primary step. This is the step number one before you do any process on silicon wafer, right? And then you need, at some point, you need, say, silicon dioxide, which is acting as a barrier or an insulator, right? And thermal oxidation is something that you can do on silicon. You cannot do it on a flexible substrate, right? This is done at high temperatures, and this also is done in a standard way because it is known that silicon can be easily oxidized, right? So for a MEMS device, you might need oxidation, right? And then you go for it. Say in microfluidics, you may not need. So these are different processes. It is not important to go in a flow. It is not important that you go through each of one of them, right? Where we talk about diffusion, this is mainly to do with whether you want some kind of P doping or N doping in silicon wafer. right? So P and N you might need in MEMS, you might not need in microfluidics, right? These are all high temperature processes. This is high temperature, this is high temperature, right? Most important becomes lithography, right? This you will need in both, whether you work in MEMS or you work in microfluidics, where you want to create some pattern, right? So when I talk about, say, a device with one input, right, but say multiple outputs. So one output is coming here, one output is suppose going here, right? So how do I make this track? I can make this track when I do lithography. So this is important in both, right? Deposition is important, right? You saw that, so suppose I make a wafer, right? And I do some kind of an etch from the back, right? So this has been removed. This part has been, this is a cross-sectional view of silicon wafer. These are, say, two anchors, right? And this is my silicon wafer. Say, suppose this is only 1 micron thick now. So this entire thing has been removed. So for removing, you will need something like etching, right? But suppose you don't want this to be removed, right? You want to protect it using some layer where you might need deposition, right? So making one MEMS device might have, say, 8 lithography, say 5 deposition and 2 etching, right? But there is no sequence. It depends on how you design it, what steps you make. It is almost like you want to draw a table on a paper, right? So it's up to you whether you make first the base or first you make the legs, right? Or you make the top, right? Or you make this leg first. It's up to you. So say as a designer, I might want to make the legs first, right? Or I might want to make the top first. The only thing is there has to be a logic as to why you want to make first the top or first the leg. It should not happen that I made the top, then there is then no way to make the leg, right? And that's what designing an experiment means like, right? And the last one that I've shown here is fusion anodic bonding is mainly to do with, say, packaging of the device. This I'll show you how it is done because it may not be so easy to explain here. Okay, so I just talked about etching in the previous slide. And so I would like to talk about some bulk and surface micromachining and why they are important in MEMS, right? So this is the cross-sectional view of silicon wafer where you have 2 layers at the top, right? So I use photoresist. So I may not be able to explain it in detail because this is not really, say, a microfabrication related presentation where so if I have to explain this, I have to explain the entire processes, which we may not be able to cover today. But in this, what is important to see is that in step C and D, you can see that this has become void, right? Now this gray part is missing here. That means this silicon substrate, which was gray part, has been etched out, right? So the entire, if you see the entire silicon wafer plus this green layer is also removed. And so this is called as bulk micromachining, right? This is your bulk. This is few microns, right? This is majority. This has been removed. And so this is called as bulk micromachining. Mainly it's done from the back side of the wafer, right? Whereas here I'm making, so this is a cantilever. Now you can see this orange color line that is hanging is a cantilever, right? Whereas here also I'm making a cantilever. I'm showing you the end product. What is the difference? So difference is here you're removing it from the back. Whereas in this case, you again have this green as silicon wafer, right? And when you want to make a cantilever, say of this black one, you've removed the white, this gray white that you see has been removed. So this is now air, right? So now this that has been removed is your hanging structure. So this is also cantilever. And this is also a cantilever. Here, the bulk has been removed. Here, the surface has been removed. And so this is called as surface micromachining because it has been removed from the top. Here you have removed the entire bulk, and so it's bulk micromachining. Yeah. So these are two standard ways of just creating, say, a structure, right? But it is not that you just take the wafer and you etch it out. Before that, you have to do deposition, you have to do lithography, right? You might have to pattern this orange layer. You can see the gray is patterned, orange is patterned, right? And then this has been removed. So important thing that you need to know is that suppose I'm removing this from the back, right? And I did not take care of this thing that this orange may also get etched out. That means this orange layer has to be such that once this is removed by an etchant, it should not attack on the orange part. Or else this orange will also get wiped out, which I don't want because that's my cantilever. So I have to look for an etchant which will only cut out my gray and my green. Same way here. I don't want the black one to be removed because black is my cantilever. So I look for an etchant which can remove white only, neither black nor green. Otherwise, they will also get removed. Then it cannot be a cantilever at all. Yeah. Okay. So coming on to this, I'll show you one device that I made in IIT Delhi. So this is a microfluidic micro mixer, right? So it's microfluidic, which is used for micro mixer application. Now, what is interesting here is that, so this is a fabrication process, right? This looks much simpler than what I have been explaining till now. So we take a silicon wafer and we do a thermal oxidation. So I have SiO2 all around my silicon wafer, right? And then we deposit aluminum using thermal evaporation, which is a deposition technique, right? And then you do lithography and I pattern. So if you see, I have removed some of the layers, right? The blue, pink, and green layers have been removed, right? And then I make channels in silicon. Now, if you see from D to E, the gray one has been wiped out little bit, right? So here I have made the track. Now I remove all other layers using etchants, right? And then pack it at the top using anodic bonding. So this is the one that I was talking about in this slide. This one, fusion and anodic bonding, right? So let's see how it is useful for our devices. Actually, why you need them. So this is just a schematic. If you see, this is the silicon wafer, right? So this one is 2 inch in diameter and we pattern it and we etch out the channels, right? Here I have 1 input, here I have 2 input, and here I have my output, right? So I put liquid here, I put a liquid here, they both get mixed, they travel, and then we take it out from the bottom, right? So this is a silicon wafer and say it is few micron deep channel. That means if I'm not taking proper care, the liquid might also come out of the channel, right? So what can I do? I can cover it. How do I cover it? I package it, right? So once you package it, this is how it looks like. Now this is on top with a Corning glass, right? So using anodic bonding, they both have been stuck together. So you can see some holes were drilled in the glass, right? So that you can reach your input port, both of them, and then output port. The difference in between this device and this device is only that here the holes you see are in glass and in this one the holes that you see are in silicon, right? But both the way they are made, then they are different. I'll not get into details of what the difference is because that becomes one another lecture only on the fabrication of these kind of devices. But both are different. So that's what it is important that whichever device you're making, you have to ensure that you have designed your process already on, say, using a pen and paper. So you're sure what comes first, what comes next, right? What will you do next? And then we packaged it in a polycarbonate housing. This is all made in the lab itself, right? So what we do here is that we give two, say, gases, right? Mix them together and take the output. Or we can give two liquids, mix them together and take the output for testing, right? First, it is important to know whether the channels are properly opened or not. That's the first test, right? Any device you make, you first want to test it to understand whether it's working or not, right? Later comes my application. So suppose I make microfluidic channel for mixing something and then taking an output, but before that I have to know if the channels are properly opened or not, right? This track should not be, say, obstructed at some point. Otherwise, nothing will flow ahead, right? And like I mentioned before that, it is important to know how the track is, if it is rough or smooth. When you etch out silicon, you do find roughness like you see here in this one, right? So these are the smaller channels and these are the wider ones, right? These are, say, 400 microns, 600, and this is enlarged view of the 100 micron wide channel, this channel, right? You can see some roughness here and there, right? So if I etch it less, you will still find it less rough. But if you etch it out more, so you're going deeper and deeper and you're finding it to be more rough, right? Okay, so these are some of the studies where, we try and see whether the flow is smooth or not, right? Whether it is noisy or not. So there's this number, Reynolds number, that we use to understand if the flow is laminar, is it in transition or is it turbulent, right? We obviously prefer laminar, right? But there can be cases, so we have to know the threshold, right? How deep I can go that it does not become turbulent. How deep in the sense, how deep I can make a channel so that it does not become a turbulent channel. Okay. So this is one other example of, say, rapid detection of, say, bacterial resistance, right? So I'll just briefly explain you. This is not my work. This has been taken from a reference, right? So here what they do, suppose I have, say this is like my cantilever, right? My AFM cantilever. So if we don't talk about AFM for a while, it is like a cantilever, right? Which will show some kind of bending, right? So suppose I want to check which are these antibiotics, right? Say 1, 2, and 3, right? If my, say, suppose, I'll give you an example. Suppose I fell sick, say, with viral, right? And I took 3 antibiotics, but nothing worked, which means that I got an infection where this antibiotic is not able to settle it, right? That means whatever infection I had is resistant to these antibiotics, right? So we want to do a study where if a person has some virus, whether they are able to respond to this antibiotic or not. So I have 3 different antibiotics. I want to experiment and see whether this virus is reacting with it or not, right? So I have, say, one, say, cantilever with virus, and I make it react to one antibody, and it does not bend. That means it's resistant to it, right? It will not change anything. Suppose the green one reacts with this green virus, then what will happen? This will slowly start to bend. And when it starts to bend is where you can see the sensitivity. Right? So you can see some kind of mechanical bend. And that's how these are called as mechanical sensors. All these MEMS-based devices fall in the category of mechanical sensors. Right? And suppose I have then the pink one, which does not react with green one. And so this is also resistant. So I know that if person A gets this kind of virus, right, may be given a green antibiotic, because this green antibiotic might get attached to it and kill the virus. Right, so this is more of, I should say, biomedical study using AFM cantilevers. But also, if you want to see this small detection, right, of this movement. So here what they did that when the cantilever is bending, it's very difficult to read micron bending, right? So they have a photodetector. So that can actually read the movement. And so what it will show you is mainly the result will be in terms of optics. Right? You will see light intensity, change in light intensity to understand how much this reaction has happened. Right? But all of these studies require a lot of sophisticated facilities. Right? For fabrication, you need a lot of, say, standard facilities. You can get reproducible results. You can get same kind of device, right? If your process is set, your equipment are working fine, you can get good results. But at the same time, you need that. If you don't have it, then it will, one device might differ slightly from the other. And that might bring a lot of change in terms of sensors. Right? Okay. So this one is also similar to what I have shown in the previous slide. It's actually the same thing only, where they have checked how this E. coli is reacting with antibiotics. Right? So any movement that you see, the cantilever deflection, means a reaction is happening. This result is similar to what I showed in the first place when I was showing how MEMS cantilever move. Right? And upon their bending, we know whether the device is sensitive or not. Right? Okay. So yeah, so this is all what I have for all of you. You can connect to me on any of the ways, right? I'm on LinkedIn, or if you have any doubt or if you want any detailed information about anything, you can write to me. I'm on this sakshi@iitj.ac.in, and I'm happy to take question and answer.
Yeah, thank you, Dr. Sakshi. Nipun, can you take question?
Yes. Thank you, ma'am, for such a nice talk. We'll take first question from Ms. Sridevi. She's asking why electrochemical sensors are less often used by clinicians than optical sensors.
Okay, oh, that's a good question though. Okay, so why electrochemicals sensors are used less? So that's mainly because, see, electrochemical sensors require a lot of, I should say, chemicals. The studies are on, see, if you do electrochemical study on the same sensor, which means it has to be exactly same as the previous one, right? Then it will be, it can be used still. But when you talk of optical sensors, which mainly uses illumination or photodetector, right? That is supposed to be very accurate. So in general, if you see, say, just the data sheets of, say, an electrochemical sensor and say an optical sensor, you will see that optical sensors are much faster and much more sensitive. But at the same time, they are not very, I should say, field trial friendly, in the sense that optics requires a lot of good packaging, and then you take it to the field, it should not catch dust and all of that. So both have their advantages and disadvantages, but electrochemical sensors are also used for commercial sensors, not that it's not used, but yes, it's only the chemistry part of it. So if you use the exact volume, the same kind of sensor in the same kind of environment, then electrochemical may still work very well in comparison to, say, our optical sensor.
Thank you, ma'am.
I hope this is the question.
Yes, ma'am. We have another question from Mr. Rajat. He is asking, in cantilever, it may also happen sometimes that target molecules falls such close to the center of mass, then torque will be lesser and cantilever deflection will also be lesser. So how this approach could work in this situation?
That is true. So when you work in the area of cantilevers, it is important to identify the region of detection, right? So if you see the region which is closer to your anchor is supposed to be more sensitive. So when you create the spot for, say, the sensing spot, right, it has to be closer to the point where you will find the maximum response. So suppose you make, say, a cantilever, right? Oh, yeah, you make a cantilever and here is my anchor point, right? I put a liquid here, right? So this deflection will be maximum noticed here. So then my reading should happen from here and not from here. But the weight cannot fall here, because if the weight falls here, then you may not get a good sensitivity. So it is just not cantilever, I should say, for any kind of sensor, it's important to know where the sensing spot is. That is important.
Yes,
Yeah.
thank you, ma'am. I hope he is clear now.
Yeah.
Yes, ma'am. We have another question from Dr. Bharti Patil. She is asking, what is the percentage of reproducibility of such devices? I think she might be asking for microfluidic devices. And also, if possible, give brief idea about wastage of material also.
Oh, wasted. Okay. So microfluidic devices can be reproducible. It's not that it cannot be. If you use standard processes and standard material, say you use silicon material, so it is possible to have same devices. I mean, all of your devices, see whether it's microfluidic or MEMS, right? If your process is set, you can get reproducible devices. Coming on to wastage, yes, wastage is there, right? So when I'm say etching silicon wafer, right? I'm say making it react to different gases, and then the waste material comes out of it and the gas also gets wasted. So that will be there for sure. But then to get something, you have to lose something. So it depends on what kind of device you're working on. If you work on, say, just PDMS based devices, there your wastage might be much lesser, but yield might go less. So it's a trade-off, whether you want high yield or you want to, say, waste less material. It depends on the substrate that you choose. But wastage will be there, that is for sure.
Thank you, ma'am. We have another question from Mr. Sumit. He's asking, if we want to have the microchip for a long time in our body, can we choose the temperature of the body as the power?
Body as a?
Power. Can we choose the temperature of the body as the power?
Oh, as a power. So it's almost like generating what energy through the body. Is it like that?
Yes, ma'am.
Okay. So I think the question is more related to energy harvesting kind of thing. So Nipun, can you repeat the question? Sorry, I think I missed some part of it.
Yeah, sure, ma'am. He was asking, if we want to have the microchip for the longer time in our body, can we choose the temperature of the body as the power?
Okay, so in our body, so it's more to do with implantable device kind of thing.
Yes, point of care applications. So.
Okay, so see, I think that these are like two different questions. So one part is about using the body temperature, as a source of energy to the device. So that depends on, suppose you're working on a wearable device or a device which requires very minimal energy to work on. And there is a way, suppose you talk about, I can sit on a cycle, right? I paddle the cycle and I also generate energy and I say charge my phone, right? So that becomes one application and that is possible. The only thing is that it depends on how much energy you want to generate. Now, in this question, like he's talking about using body temperature, right? So if the body temperature stays constant, which is a rare case, right? So only a minimal value you will be able to use for powering your device. Now, if your device is okay with that small energy that you can get from your body temperature, then it may be possible. But then it's still a very research-oriented, a challenging question because it more depends on how much energy you need, right? But there are ways of generating energy through physical motions. All that is being worked upon. So that is possible, but then one needs to do more research to figure out if this can be used for this application.
Thank you, ma'am. Thank you for your response. We have another question from Mr. Ashok. He wants to ask what is the most efficient technique for eliminating air bubbles in the microchannel?
Oh, so if you want to eliminate air bubbles, which is a very common problem that happens. So one is that you say suck in the entire air before you actually put your sample. So it's almost like creating a vacuum, right? And once that is done, then you push in your sample. So there are these micro pumps which are available, which you can connect to your microchannel devices and the air bubbles can be removed. Yeah.
Okay.
And one needs to ensure that when the sample is actually going in through the channel, like you do it for actually any kind of say a pipette, right? When we take sample in a pipette, we always make sure there is no air bubble. So we have to do it really slowly. It's the same process. So it's more to do with using a machine and plus the expert. So one has to make sure that you do it slowly so the air does not get in through the liquid when it is passing through the channel.
Right. Thank you. Another question he wants to ask how to avoid backflow in microfluidic PDMS channels.
The backflow.
Yes, backflow.
Oh, backflow. Okay.
Yes.
So yeah, the flow will go from like it goes in a normal environment if I talk about, right? If it is a high pressure at the top and low pressure at the bottom, right? It will just fall off. So the same way here also you have to just maintain the pressure difference and it will flow off. So that should not be a problem. Yeah, once you inject from one side, it will always find a way out. But yeah, gravity doesn't work in microfluidic channels. So you maintain the pressure and it will flow.
Right. Thank you, ma'am. We have another question from Miss Nidhi. She's asking how precise results we get in ELISA test.
How precise test you get in ELISA test?
Yes.
So ELISA test, yeah, ELISA test is more to do with the reader that you use, right? The ELISA reader. It is possible to get accurate results. It's not that it's not possible. And I should say it depends on the reactions that one is putting in. So say I use antibody and antigen, right? And suppose that antigen is not very specific to the antibody, which also happens in a lot of cases. In that case, accuracy might be affected. But if you do a good reaction, then it's possible to get 99% accuracy from ELISA. It mainly depends on your reader, which is reading the color of the test. So if that is accurate, then it should be good to go. Yeah.
Thank you, ma'am. I personally want to ask one question. In one of the slides, I have seen that there was segregation of the fluid in droplets. So was that because of some kind of external field applied or some property of fluid was there due to which there was fluid was flowing out? Fluid was not continuous, it was flowing in droplets.
Right. Yeah.
Yes.
So that can happen mainly, say, if you're using a fluid which can be separated using charges, right? So one terminal I can give positive and one terminal I can give negative. That becomes the easiest way to separate or say concentrate my analyte, right? The other can be weight based, that I have heavier ones on one side and lighter ones on one side. So that can be based on weight. It can be based on electric properties, which are your positive or negative charges, or it can be through magnetic also. So suppose I want to have these iron nanoparticles, ke saath I tag something, and then I want to put it on one side, then I can use magnet on the external side of say a beaker, right? So all these iron nanoparticles with the tag will move on to the magnet side. So there also I can do some concentration. So it can be weight based, it can be property based. Yeah.
And then how can we have electrodes on the, is it on the microfluidic chip or beneath the microfluidic chip or over the microfluidic chip?
You can have it on both actually. So you can have it say on the silicon wafer if that's the base of the chip, right? You fabricate it and then you package it. One way is to do it, say under. Wait, I'll show you. Wait, what? Here, I'll show you. So one way is I make the electrode under this glass, right? So this is a glass and bottom is silicon. So one is I make electrode here inside. The other option is I make electrode on at the bottom side of the glass. So I can make electrodes on by two ways. One is on the wafer, the other is on the underside of the glass. It's mainly deposition only, whether you do it on wafer or you do it on glass. So some people use such bioanalytes, say they react with, say silver. I use a silver electrode, right? Or I use aluminum. Then I can't have these analytes touch the electrode. So I have to make my track away from the electrode so that they don't interact. It is only for measurement purpose. So best is you have it on silicon because you can just do it with your silicon processes. Say chrome gold deposition or aluminum or silver.
Okay.
So you can have it on both. Yeah.
Thank you, ma'am. Ma'am, one of our participants wants to ask your question. I will just unmute him. Hello, Abdul. Hello, can you hear me? Hello. Hello, Dhananjay.
Yes, yes, audible.
Yes, please. Yes, please go ahead.
Ma'am, I can take some little 5 to 10 minutes because I have some little question is there. So what about biomimetic biosensor? Means when you're talking about MEMS, can you make the biomimetic of a MEMS? Mean take example of a mimosa pudica, a tree which is called a same tree. So the concept what is behind the tree, if you take the mechanical concept and use in the device, so is it possible to make a biomimetic biosensor?
Well, it is possible to, but what will be the input and what will be the output of the sensor?
No, basically before going to, as you told that before going to design anything, first you need to draw the diagram.
Correct.
So before going to MEMS,
Correct.
you should know the mechanical things. So my plan that
Right.
like so much of bio things is there which have a different mechanical property. Like one example I gave a mimosa pudica. Till now I have no idea about the application part, but I want to find the mechanics behind the bio thing. So can you copy that bio things and you can use in mechanical system for MEMS?
You can do that. So if I think you're talking about checking the design first before fabricating it. Am
Yes.
I right?
Yes.
Okay, so that is possible. So there are some softwares where you can actually simulate these devices before you actually take them to, a fab lab or at the physical level. So that is possible. So there you have to see that the choice of materials you're looking for, if they are available. So it is possible that you might find, say, PDMS, but you may not find some ABC material that, say, you have made, right? Because it does not allow that much of customization. But if you talk about standard materials and some of the biomaterials, they are available in the software and you can simulate it first and also study the, say, the flow or the movement, right? The mechanical movement, how much it will bend, how much temperature it will have, right? Whether it will get heated up or not. Everything you can check before you actually go for fabrication.
Okay, ma'am. So next question, ma'am. When you discuss about this cantilever system, there is two type of stress. You can say that normal stress and shear stress. So different till now, it's cantilever people doing work on related to normal stress. Why not people are working on shear stress? Is it possible to design or not?
So with the normal stress, see, what also needs to be understood is that when any kind of molecule that is going on the cantilever is bringing a major effect on what, right? So if you see that where you're, like I was showing it here, where you, sorry, just a second. So where your molecule will fall, right? I hope you can see my screen.
Yes, yes.
So molecule will fall, right? And what kind of bending will happen and what kind of stress will be generated at that time, that becomes important to study. So that's why this normal stress is mainly studied, because this is the one which gets mostly affected. So if even if you say want to work in cantilever and want to understand these different kinds of stress also, right? That
Yes.
also you can study through the software. This is mainly the commenterware software, where you can have you can make a cantilever of a material of your choice. You can give the dimensions and then you can put some weight on it, right? So that weight may not be exactly coming from, say, a biomolecule, but that weight will be in somewhat in micrograms or nanograms. And then you can see the amount, the way the stress is being affected and which one is majorly affected, because that is the one which will actually be read when you put your biomolecule. So that study you can in the simulation.
Yes, ma'am. And ma'am, about your work, as you show that one your work process before to 5 to 7 slide. My question is that why you choose this much turning thing? Yeah, that. No, ma'am. Go forward. Next. Yeah. So is this much bent you told. So is there any specific motto you have to make this much diagram? Means
This one.
yeah. No, this much turning means
Okay.
like zigzag types you make.
Like this,
Specific
the
motto about
serpentine, you mean?
yeah.
Right. So yes, this has a purpose. This has a purpose. So suppose I put my input analyte here and here, right?
Okay.
So the aim of this one was that I want to mix my input 1 and input 2, right?
Okay.
And I want to give them sufficient time to get mixed up. So one is that I just make 2 input ports, a straight line and output. In that case, I might get the response in, say, 2 seconds, but the mixing may not happen so well. So here we made, these are called as serpentine channels. So here you go zigzag, you go on the right and then you move all the way back to the left and then come back, right? So this goes and this makes a lengthy channel. So there was a reason why it was made of this length, and then why some of them will be narrow and some of them will be wider. This also was worked upon using this. There is a, I should say, there is a concept in microfluidic theory where you have to, so there are some equations which help us understand the flow of the fluid in these channels. So we do those calculations and then decide that X number of channels I need, say, wide, and Y number of channels I need narrow. And then we club them together, and this is the length of the channel that I get in which the liquid will flow. So for a mixing device, it's best to have lengthy channel so that you're giving them sufficient time while they're traveling, they're also getting mixed up.
So this design is based on this mathematical equation. Am I right?
Yes.
So ma'am, when we were discussing about the software analysis before doing the man, so will it COMSOL be the best one to use for the analysis?
More than COMSOL, I think, yes, I think yes. COMSOL Coventerware should be good to understand the mechanical part of it. The material, mechanical, temperature, the stresses and all.
So this is for both MEMS and microfluidic for both processes.
That's mainly for MEMS, mainly for MEMS. Microfluidics, only if that module is available, then some part, yes, can be explained. Otherwise, microfluidics can also be understood using just the mathematical equations. So you have to know the shape of the channel, the cross section of the channel, whether it is a trapezoid or it is rectangular or circular, how long, what liquid will pass through, how viscous it is. All that needs to be known. And then you can do it even with mathematical calculations.
Ma'am, rather than this, yes, ma'am, thanks. Then rather than this cantilever concept, mechanical concept, is there anyone mechanical concept but what you can use in biomems or microfluidic or MEMS you can say?
In the using the cantilever one?
No, beyond the cantilever. Because you are generally, we know that mechanical means you are choosing cantilever and doing that, but so much mechanical things like rotational, vibrational.
That's true. Yes, yes. You can use piezo materials. You can use piezo resistor. You can use capacitors. So there are lots of ways of doing it. It's not just restricted to cantilever. Just that cantilever is the one which is, say,
For basic-
easier to
Yeah, I see.
understand. Yeah. Yeah, but you can use piezoresistive materials, piezoelectric materials. There are lots of ways.
Okay, thank you, ma'am. Still, I have some question, but I will send to my mail because I need to walk. So,
Okay,
thank you.
sure.
Thanks, ma'am. I'm very happy
Sure.
for discussing about this thing. Thank you.
Thank you.
Yes, Nipun, any other?
Yes,
Can take one
yes,
more
sir.
question. Yes.
Okay, okay. Dr. Neha, can you listen me?
Yes, sir, I can listen.
Yes, yes, please go ahead.
Okay. Good afternoon, ma'am.
Hi, Dr. Neha.
Yeah, ma'am. Ma'am, actually, I'm having two questions. I had designed my PhD optical coupler microfluidic channel for detecting some like analyte. It was heavy metal ion. Ma'am, I have designed that, but I need to know, okay, can that particular thing be simulated in, like, I was trying to simulate that in the console, but that was not possible. Because I can only simulate either microfluidic channel, I can analyze the flow and all, or I can simulate the waveguide. Can I club these together, and is there any software related to that so that I can see my like experimental thing on the software? Is there any software known to you?
So you want to club both of them and see the response?
Yes, ma'am. Suppose I want to flow some analyte to the channel. I want to see the change in the analyte. Suppose it's a concentration. And through optical spectroscopy, I want to analyze that. Is there any software related to that?
I doubt it because these two are different things.
Yes, ma'am. Yes,
right?
ma'am.
So it's like part A and part B.
Yeah.
So doing it together, doing it together, it's like simulating the whole system.
Yes, ma'am. Yes, ma'am.
So that I'm not sure of if that can be clubbed and checked at one place. Yeah.
Oh, okay. And then my another question is, like, we are using glucometer for sensing the glucose level in the body, na, by injecting a needle and taking that. So, ma'am, by changing the strip, that is the electrochemical sensing that is happening, like amperometric sensing is happening. Then by changing that strip, can we use that glucose like a sensor for any other analyte detection? Like if we change the strip with another in glucometer, like glucose oxidase is immobilized onto the electrode for detecting the glucose. Instead of glucose, when I detect uric acid, suppose uric acid I want to detect, by immobilizing the uricase enzyme, just changing the strip, remaining portion is same. Can we do that, or we have to change the entire system for that? Signal processing and all we have to change.
Right,
Is it
right. So if you change the strip and surface chemistry and say the output coming from the strip, right?
Yes. Yes,
So
ma'am.
then it may not be possible because that readout, that machine that is made is calibrated as per the results they got from the glucose strip.
Okay, ma'am. Suppose like in that also only flow and the current will be changing, like electron will be generated or
Correct.
combined. From that,
Correct. But the number of electrons that are generated, say from your strip, right, that you want to work on
yes,
for urea, but it may not be same as the current that will be generated, say by the glucose oxidase strip. So in that case, the readout, which is, that has like a chip that already knows that if this comes, this is what I have to display. If the input of that readout has changed, then it will give you result as per the glucose oxidase strip only. Only if the number of electrons are same, like they were in the glucose oxidase strip, only
yes,
then
ma'am.
it will show the same result. Otherwise, it will not show the same result.
Okay, ma'am. Ma'am, actually, I was thinking instead of changing the entire setup, we can change the strip thing and we can use that for all in one kind of sensor. But that is not possible. You have to change the circuitry as well, right?
Yes, yes. Otherwise, that company which is making the machine will understand that people are trying to use it for different applications.
Yes, ma'am. Okay, okay, fine. And then my one last question is, like we were using PDMS polymer for creating the channels and for detecting the analyte. But after using that for 10 to 12 times now, ma'am, because of the dust and all, the PDMS channels were like they were not as they cannot be used after 10 to 12 run. Is there any like how to clean that out and we can use that for another run or something like that?
So PDMS is generally very easy to make and it's low in cost.
Yes, ma'am.
So
Ma'am,
that
suppose.
way, I understand. Yeah,
Yes, ma'am. Please
yeah.
continue.
Yeah, so I was just saying that PDMS is otherwise like a disposable kind of
Yes,
a chip,
ma'am. Yes, ma'am. Yes, ma'am.
right? So instead of cleaning it, I would suggest to use a fresh one because,
Okay.
yeah, yeah.
Okay. Okay. Okay, ma'am. Yeah, that's all, ma'am. Thank you so much. Yeah.
Yeah. Okay, okay, Dr. Mia.
Okay. Yeah. So let me thank Professor Sakshi for this excellent talk. So thank you very much.
Yeah, thank you, Dr. Mahesh. It was great coming here.
Yeah, thank you. Thank you very much. So now we will continue this one. Next talk is by Professor Pawan Kuleria. This is the most awaited talk on hydrogen sensors. So yeah, Professor Kuleria, are you?
Yes, yes. Good
Yes,
afternoon.
yes. Good afternoon. Yeah. So Nipun, yeah. Can we start?
Yeah, sure, sir.
Yeah, please.
So moving on, I would like to welcome our next speaker of the event, Professor Pawan Kumar Kuleria. Dr. Kuleria is working as an associate professor in physics at the School of Physical Sciences at Jawaharlal Nehru University, New Delhi. Before joining JNU, he was associated as Scientist F in the Material Science Group, Inter-University Accelerator Center, New Delhi, India, for 17 years. He holds both PhD in Physics and MTech in Solid State Materials from IIT Delhi and an MSc Physics from the University of Rajasthan, Jaipur, India. He was awarded prestigious Fulbright Nehru postdoctoral fellowship by the US Department of State at the Rensselaer Polytechnical Institute, USA. Dr. Kuleria has over 150 peer-reviewed papers in leading international journals and about 100 articles in the conference proceedings in his credit. He established in situ X-ray diffractometer facility in the particle accelerator beamline at IUAC, which is a unique facility in the international scenario. He is a member of various professional societies, including the National Academy of Sciences India, and served as Joint Secretary of Indian Physics Association. His research on experimental condensed matter physics includes nanostructural materials for nuclear and hydrogen energy applications. So with this kind introduction, may I request Professor Pawan Kumar Kuleria to deliver his lecture for us. Please, sir, over to you.
Yes, yeah. So thank you very much for nice introduction. So I will share
Thank you,
my
sir.
PPTs and then we will start it here. Yeah. So my PPT is visible.
Yes, sir. Yes.
And what about my volume? Am I
It's
audible?
clear. Yes, sir. It's very much clear, sir. Please proceed, sir.
Yeah. So good afternoon to all of you. And first of all, I would like to thank Professor Mayesh and all the organizing committee meeting, all the organizing committee member to inviting me in this prestigious workshop. And I am coming from School of Physical Sciences, JNU. And today that topic that I have selected for this workshop is that is related to renewable energy. That is one of them is hydrogen energy. And in that one, I will try to explain you what is the role of nanotechnology to design a sensor materials and that have a better performance or like that one. So in that one, I have selected palladium nanoparticle based hydrogen gas sensor. That title I have selected it. Just a minute. Yeah, I'm changing slides. So in I think. Yeah. So for Indian participate, JNU doesn't require any introduction. For just for completion, I would like to mention it here. Like as per NIRF ranking, so we stand number 2 ranked among all the universities in India, and among the central universities, JNU stand number 1. And at JNU School of Physical Sciences, I am taking care of this Advanced Material Research Laboratory. And in this laboratories I will briefly explain about the area that we are working before I start my formal 2 days talk. So mainly that area that we are working is related to material design for nuclear reactor applications, as well as material for gas sensing applications. So in that one, you know that there are materials that being used for nuclear fuel are uranium dioxide, plutonium dioxide, and thorium dioxides. And when these fuel pellet, they are loaded in nuclear reactor. So at that time, the grain size of these particle, it is in micron size. But when these fuel pellet are exposed to the nuclear reactor for 3 year or 4 year, so after that, these fuel pellet, there is a grain fragmentation is there, means micron grain is fragmented to the nano grain. And as a result of that, mechanical property of the fuel pellet is degraded. So that's why there is a need to design some advanced nuclear fuels so that can have a longer time or like that one. So that this one is one of our core area of interest. In addition to that, you know that in nuclear energy, main problem is how we can dispose the spent nuclear fuel that is coming from the nuclear reactor. So that is another area that we are working in. That one we are designing some advanced materials, and that material is a pyrocross structure material. And these material can be used for disposal of the high level waste that is coming from the nuclear reactor. And our another area that we are working is that is again have a application in nuclear reactor, because you know that nowadays that nuclear reactor is being used. So in that one, mainly stainless steel is being used for as a vessel. But the advanced nuclear reactor, like they will be have a much higher power. So in that case, these reactor material will be exposed to a very high dose of the radiation, and as well as temperature will be very high. So in that case, that normal steel that is being used, that cannot be used it. So we need some materials that have a very good mechanical strength and as well as structural stability at extreme condition of like high radiation as well as a high temperature. So these are 3-4 areas that we are working in. And recently we have also started this new area that is nanostructured material for gas sensing applications. So today, as per the title of this conference or theme of the conference, so mainly I will concentrate on this nanostructured material, particularly this palladium based material for gas sensing applications. So this will be outline of my talk because as per my discussion with Dr. Mahesh, So most of the participants are the graduate students. So I decided like that. So I will explain about what is the palladium hydride interaction and how that palladium hydride interaction we can use to design a material for hydrogen gas sensing applications. Then I will discuss about palladium thin film for hydrogen sensor. Then again we reduce the dimension from the 2 dimension to 1 dimension like nanoparticles. And then I will discuss about palladium carbon based nanocomposite material for hydrogen sensing application. In that one, how we design the thin film and then how we analyze by using various characterization technique like Rutherford spectrum spectrometry, SEM, TM, synchrotron XRD, and sensing response. And then finally, I will conclude my talk. So now, what question is coming? So what is the need of hydrogen energy? So as you know that, particularly in our country, most of the energy that we are getting is either from the hydro energy or from the fossil fuel. And from these fossil fuel, a lot of pollutant is emitted in the atmosphere. So as a result of that, local air quality is degraded, and there is and most of these petroleum products that we are importing from the other countries, okay, and that also creating problem in payment balance. And most important thing is that they are polluting our environment, and they are affecting the global environment changes or like that one. So that's why there is a need for a clean source of energy. And in that one, hydrogen is most important in that one, we can say like that one. So that's why there are a lot of scope to design a material so that can be used for hydrogen production as well as hydrogen storage and hydrogen sensing or like that one. So if you will go for production of the hydrogen source, so these are the main source, like 40% of hydrogen gas is produced through the natural gases, 30% from the oil, 18% for coal, and 4% from electrolysis. And this production rate is every year is about 15 million ton, and that is growing every year by 10% or like that one. Okay, so if I will compare hydrogen fuel with other fuel like that petrol, diesel, and that we have. So if you will compare in that one, you will find that it have very good properties in comparison to other fuel like that one. It is it one is a best clean source of the energy. And then if you compare the heat of combustion like that one, so in case of the like petrol, diesel, or other fuels, so it has about 3 times like 142 kilojoule per gram. So that is very high. Or we can say like among all the fuel, hydrogen have highest heat of combustion energy. Then it have a very low ignition energy, that is 0.017 millijoule. And it has a wide flame range, like between 4 to 75% or like that. And most important thing about hydrogen energy is that so the final product or combustion product of this one is water. So that is most important for our environment point of view. So this one is just a schematic diagram showing the hydrogen fuel cycle. So like that, if you have water, so you can throw sunlight on that one, and as a result of that, by hydrolysis, you can able to create the hydrogen. Then you can store the hydrogen, and after that, that hydrogen can be used in a fuel cell for transportation of the vehicle or like that one. And final product in this case will be water. So that way, in this diagram, it is clearly showing like this is a one of the cleanest fuel that hydrogen energy have. But there are some issue with the hydrogen energy, and that we have to take care of. First and most important thing is that hydrogen is a colorless. So by naked eye, we cannot able to see it. And it is odorless and tasteless. So due to these properties of the hydrogen, it is very difficult to detect the hydrogen gas if there is any leak is there. Then another important property of the hydrogen is that it is, you know that it is the lightest element among all the elements that we have in periodic table, or we can say it is the lightest gas. So that's why, because the size of the hydrogen atom is very small, so that's why it can easily diffuse from the source of the leak. Okay, so that's why it is very difficult. Means suppose if you use hydrogen energy for transportation, and if there is any leakage is there, so due to its small size, it can easily transport in the atmosphere or like that one. And another important thing about the hydrogen energy, that it is explosive in the nature. So like that, if the concentration of the hydrogen is more than 4% in air, so then it can lead to explosion. So that's why it is very dangerous, or could be dangerous if we could not detect hydrogen or like that one. So that's why detection of the hydrogen is very important due to safety issue in large number of the public or application that we want to use it. So due to these associated issue, and particularly this explosive nature of the hydrogen gas, so it is very important like that we need some high efficiency sensor, so that even a very small quantity like ppb or ppm level quantity concentration of the hydrogen we can able to detect in the atmosphere. Okay, so for that we need a sensor. So because from last 3-4 days you are already people are discussing about the sensor, so I need not to explain it in detail what is the sensor. Basically sensor is a technological device that detect or sense a signal or physical condition or a chemical compound like that one. So any device that convert a signal from one form to another form, that we can say as a sensor. And mostly that sensor that is available for detection of the gases are they are either as electric or electronic sensor that we have. So because as a material scientist means when we design any materials, so we have to keep in mind what is our aim, means what is our limitation or like that one. So if one want to design a sensor specifically for a gas, they are very explosive in nature. So one have to keep in mind all these 8 parameters. Like first and most important thing is the detection limit. So any material that we can select for a gas sensor, so detection limit should be very low, means as minimum as or as small as quantity that we can able to detect by using that material. Another thing is it can be have a very good temperature stability, because it may be possible like that one we need to install these type of sensor in a like in extreme environment or like that one. So that's why it should have very good temperature stability, as well as it should also have stability under humid environment or like that one. Then another important parameter is the response time. Means suppose we design a material, it's have very good detection limit, but if its response time is very large, maybe like 10 minutes or 15 minutes, so in that case, that material is useless for us. So like that response time of these type of sensor, whatever that we are designing, it should be as low as possible. If it is in millisecond, and then it's great. But otherwise, our aim should be like that. It should be as low as possible. Then another important thing is the sensitivity. Sensitivity means like that signal that we are detecting. So how much there is change in the signal strength. Like for example, like if you are detecting sensor by measuring the resistance of the material, and let us assume that resistance of the material in the beginning is like it may be 10 mega ohm. So when I expose to a particular gas, and then if resistance is changing from 10 mega ohm to like 10.1, so it means that for detection of these type of very small signal, it is very difficult. Or we can say like 50 ohm, and then it will become the 51 ohm or like that one. Okay, so if there is only a very small change in the that resistance on exposure to the hydrogen gas or any gas is very small, then it will be very difficult. And another thing is its reversibility. Reversibility means that sensor that I will want to design it, so it have capability to reuse it. So it is again related to the sensitivity like that one. For example, if resistance of my material is 50 ohm and on exposure to the hydrogen gas, suppose it become 500 ohm, then I will remove it. Then again, whether it come to a 50 ohm or whether it is a 200 ohm or like that one. So if it is 200 ohm, then you know that after 2-3 cycles, it will be reached to the 500 ohm, and then I cannot able to detect it or like that one. So that material that we are selecting, it should have capability like that, whatever that gas is going inside the material. So maximum amount of gas we should able to extract it or like that one by either means, like either we can able to increase the temperature to remove the gas, or we can create the vacuum or like that one. Okay. And then most important is this low power consumption, because these type of sensor they will be installed in a particular building or at any they will work 24 hours. So if they are consuming lot of power, then it will be very difficult for industries to mount these type of sensor or like that one. And then another thing is that that material that we selected, it should sense that particular gas at room temperature. Okay. So that's why if suppose we have designed a material so that have all good properties, but it can able to sense a gas a particular temperature like 200 degrees centigrade or 300 degrees centigrade. So it means that I need to maintain my sensor material at each time on every day or at each time, like at a high temperature. So that will be very difficult. So that's why the material that we are going to select it should work, or it should able to sense the gas at room temperature. So these are the 7-8 parameters. So any material that we will select for a particular sensing gas, it should qualify all these 8 parameter. Then only we can able to say that this material is very good. But it is very difficult, because to select a material that have all good type of properties, it is very difficult. So we have to compromise on one and another, and that's why this R&D come into the picture like that one. Suppose response time is very slow. So as a material scientist, we can change the parameter, and by which we can improve the response time. Similarly for the detection limit and other parameters. Okay. So in case of this thing for detection of the hydrogen gas, so there are various means by which you can able to detect the hydrogen gas, and various material is being used. So the material being used for detection of the hydrogen gas are semiconductor like tin oxide, zinc oxide, titanium oxide, niobium oxide, indium oxide. So these are various type of oxide they are being used. So detection of the this one. Then there are some materials, so they are giving this thermoelectric response like nickel oxide doped with lithium and sodium. Okay, lithium doped nickel oxide, or it is stabilized zirconia, or silicon, or silicon germanium. Then there are some methods or materials that can be used electrochemical process for detection of the hydrogen gas, like uh, polypyrrole nanofillers coated with the iron chloride. Okay, platinum oxide, polyaniline, and CNT modified palladium nanoparticle. Then there are some ways by which these material are giving optical signals, means they emit the light when they are exposed to the hydrogen gas, like tungsten oxide, palladium coated, this one. And then there are few materials like pure metals, like mostly noble metal like palladium, platinum, gold, silver, copper, and their alloy. So these material normally they will give they change, their resistance is changing when they are exposed to the this hydrogen gas. So now I will try to compare the various parameter that I explained, and which material will be best suited for our application or like that one. So suppose if we consider the tin oxide, so that tin oxide, if I will take as a sensing material, so in that case, if you can see, response time is between 2 seconds to less than 10 seconds or 15 seconds. Again, it will depend which method that we are going to use for preparation of the tin oxide thin film, like whether it is sol gel annealing, or spray pyrolysis method or like that one. And in this tin oxide based sensor, that working temperature that you can see, this one is very high, because as per our requirement, any material that we are going to select it, it should work at the room temperature. So normally you can see in this case, although the detection limit is relatively good in this case, and then this one is again single crystalline tin oxide by they are prepared by using RF sputtering. And then these are the some doping that has been done in the tin oxide. So this one is indium oxide doped with the tin oxide, and then single walled carbon nanotube that is doped in tin oxide, and then this pure metal has been doped. So among these, if I will compare it, then you can see in doped case like this one, indium doped tin oxide. So in this case, that operating temperature is 22 degree. So it is relatively good, means it is room temperature. But the again problem is that response time, it is hundreds of seconds. Okay, so that's why if we will tune one parameter, then another parameter will be affected or like that one. Same thing in case of this one, like in CNT doped tin oxide. So in this case, working temperature is very high, but response time is very good. Okay. And for these metal doping or palladium doping, in this case, both the response time, working temperature, again, it is like 50 degree near to room temperature, but again, response time is very high. Then there are another type of material like zinc oxide. Again, it is doped with the aluminum, and these are the zinc oxide nanowires, and magnesium doped zinc oxide. Again, here we can see that response time is very high, and as well as the this operating temperature is very high. Okay, then the another oxide like titanium oxide in different, they are prepared by different technique like thermal oxidation and anodic oxidation and microwave or arc oxidation. So in that case, again, the response time is relatively high, because then there are another material like niobium oxide and tungsten oxide. So in this case, in case of the niobium oxide thin film, that working temperature is 20 degrees centigrade, but again, response time is very wide. So that's why if I will compare with all the oxides, so in most of the oxide, there is a problem of either the working temperature is very high, or the response time of these materials is very high. So that's why we need some another materials that can quantify for these two type of properties. So, so if I will consider the palladium in this case, because palladium is a pure metal and it is considered in the noble metal category. So that's why it is highly stable. Interaction of the palladium with the hydrogen, if you can say, so it has a selectivity towards the hydrogen gas. Means if there are different gases is there, so palladium will interact only with the hydrogen gas. It will not interact like if nitrogen is there or like that one. So that's when it is highly selective towards the hydrogen gas, and then it have very large sticking coefficient, that is 0.6 at 450 Kelvin, and it has a very low activation barrier for the absorption. It is like 10 kilocalorie per mole, and it has a very high diffusion rate for the hydrogen, like 2.9 10 to the power minus 3 centimeter square per second. So these are the good property, or we can say these are the favorable property of the palladium towards the hydrogen. So that's why a lot of work is being going on in this direction for design of palladium based hydrogen gas sensor. So now I will briefly explain how the palladium is interacting with the hydrogen and why it is important. So for example, like this one is my substrate. Okay, it can be a silicon substrate, and on that I deposited a film of the palladium. And then this film, if I will expose to the various gas like nitrogen, hydrogen, carbon dioxide, and oxygen. So in that case, palladium will only interact with the hydrogen. Okay, and then that is a selectivity of the palladium. And then another important thing about the palladium is that here not only palladium will interact with the hydrogen, it will also dissociate molecular hydrogen into the atomic hydrogen. So here palladium will also work as a catalytic. So it is not only selective, it is also work as a catalytic So it dissociate molecular hydrogen into the atomic hydrogen, and then this atomic hydrogen will be diffused inside the materials. So this one, this atomic hydrogen will stick to the palladium surface, and then it will form the palladium hydride. When we are removing the hydrogen gas, it can be removed temperature for removing this one is around 50 degrees centigrade or like that one. So near to room temperature means you can slightly increase the temperature of the sensing material, and then gas will be automatically come out. Or you can create a very rough order of -2 millibar or like that one. So with this vacuum, this gas will be removed from the sensing material. So in that case, this desorption hydrogen atom that is at the surface of the palladium, so they will be removed, and again they will form the molecular hydrogen, and finally it will be removed like that one. So main thing that I want to highlight in this one is here palladium is doing dual role. First thing is that it is very selective toward the hydrogen gas, and second is that it will dissociate molecular hydrogen into the atomic hydrogen. So that's why palladium is very important, and it have highly selectivity toward this gas. So now I will discuss one case about the palladium thin film. So I need not to explain about the thin film because mostly students know it. So this one is the sensing response like this one. Suppose I can take a silicon, and then you know that on silicon there is a silicon oxide native layer is there, and then we can deposit a thin film. And here I am assuming that this is a continuous film. Continuous film means thickness of the film is more than 20 nanometer or like that one. So it can be between 20 to 100 nanometer or like that one. So that is the case. And if we can take a contact from the top of this film surface, and then if you will expose to the hydrogen gas, then you will get this type of curve like that. So this one is the change in the resistance, and this is the time. So as soon as you switch on the hydrogen gas, its resistance will be increased. And then when you will remove it by some pumping mean, then it will decrease it. So it will increase it or like that one. So this can you can expose to the palladium film maybe more than 100 cycle, and even after that it will retain its structural integrity or like that one. Okay. So in that one, if you will see the phase diagram of the palladium hydride phase, so in that case you will see palladium will exist in two phase, alpha phase and beta phase. So when we expose to the hydrogen gas to the palladium at a very low concentration, then first it will convert to palladium alpha hydride phase, and finally it will go to the PDS2. Okay. But when we are removing hydrogen gas, then beta phase will convert into the alpha phase, and then finally they will move it like that one. So second time, if I expose to the hydrogen, again alpha phase will convert into the beta phase. So there is a switching between alpha phase and beta phase as we are removing and exposing to the hydrogen gas. So in that case, if you will measure the sensing response of this type of material, so basically this sense response time that can be measured by how much there is a change in the resistance. So what we will take it that we will take initial resistance, and then how much time it is taking to attain the 90% of this value. Okay, so that time is known as a response time. So for palladium thin film, it has been observed is the response time is between 15 to 20 seconds or like that one. So if you will compare with the nanoparticle in next slide that you will show it. So there you will see response time is better. So in this case, we can say it has a relatively slow response. And in addition to that, if you see the change in the resistance, so that is only a percentage change that you can see. That is again around 6 or 7% it is increased. So that's why sensitivity of the palladium thin film is also relatively low. So both the parameter like response time and sensitivity in case of the palladium thin film is relatively small in comparison to that we will discuss in case of the nanoparticle. So now I will discuss about the nanoparticles. Yeah. So nanoparticle, I need not to explain in detail because you know that if the dimension of the any material is less than 100 nanometer, then it is considered as a nanomaterials. And the reason for that one is that if we decrease the size below 100 nanometer, then the number of the atom at the surface is large in comparison to the core of the any particle. So that's why the surface phenomena will be very important in that case. And in case of the sensing, that play a very important role. So you can say like these are the different dimensions that we can see, like 3 dimension we can say as nanoparticle, then 2D is nanowire or nanotube, then thin films and nanodot. And just for for student, I would like to mention like that when you know it already, it is because the size of the hydrogen atom is 0.04 nanometer or 4 angstrom, that we can say like that one. The size of the protein is around 20 nanometer, and size of the computer chip is around 180 nanometer, and size of the human hair is around 10 microns. So that way you can get idea like in which range that we are talking here. So main important of these nanoparticles is that as we decrease the size, so number of the surface atom is increasing. So for example, from this curve, you can say this one is the number of the surface atom, and this one. So here you can say this is the particle size. So this particle size is varying between you can say around 15 nanometer to less than 5 nanometer. So if the particle size is less than 5 nanometer, then you can see that maximum number of atom is at surface atom. So their concentration will be between you can say 90 to like 40% or like that one. Okay, so if the particle size is 3 nanometer or 4 nanometer, in that case, so we can say 60 to 70 percentage of the atom will be at the surface atom. So that's why if we want to design any sensing material, so our size of the particles should be as small as possible. Similarly, you can see in this curve like that one. Again, you can see if the particle size is above 15 nanometer or like that one. So you can say in that case, maximum atom will be only at a bulk atom or like that. So that's why on the basis of that, you can define what is the what is the definition of the nanoparticle, why it should be less than 100 nanometer only, because in that case, the number of the surface atom, they will play a critical role. And if that is the case, then there are many properties of the material like melting point, boiling point, band gap, optical property, electrical, magnetic, and structural property. They will be changed, or they will be so the entirely different behavior than they are in the bulk case. So for example, like in case of the gold. So in bulk case, the color of the gold, it is in yellow color, but if the size of the gold nanoparticle, if it is less than 1 nanometer or like diameter is 1 nanometer, then the color of the gold particle it will in red color. So that's why by reducing the size, we can see some exotic properties that could not be observed in case of bulk material. Same thing like in case of the magnetic property, like palladium, that is it is a paramagnetic if you will see in bulk material. But when you reduce the size of the palladium nanoparticle to like 2 or 3 nanometer, so in that case, same palladium will show ferromagnetic behavior. So just by reducing the size, you can able to change from the paramagnetic material to the ferromagnetic material. So these are the various applications of the nanoparticles. So I will not go in detail. So mainly our concentration is to use these nanoparticles for the sensing applications. So this one is case again. I will try to explain this on the basis of schematic diagram only. And if you want to see detail, then you can go through with your these papers. In that one, we have explained all the detailed mechanism or like that one. So in this case, that in case of the thin film that we have seen, as we expose the this palladium thin film, then resistance is increasing as we expose to the hydrogen gas, and when we removing it, then it will decrease it. But in case of the nanoparticles, you can see we have see this some spike-like phenomena has been observed. You can see. So this one is hydrogen. As soon as we switch on the hydrogen, then suddenly its resistance will increase it, and then automatically it will decrease with the time, and that time span is very short. Okay, so it will show just like a pulse-like response has been observed in case of the nanoparticle. and how one can explain these pulse-like response of the nanoparticle. So that can be explained like that one. So in the beginning, we can assume these nanoparticles are well separated, okay, and they are partially connected. So as soon as we expose to the these palladium nanoparticle with the hydrogen gas, so then this palladium will absorb the hydrogen gas, and as a result of that, hydrogen gas will be go and sit in the interstitial position of this one, and that lead to change in the resistance of the material, okay, and there will be lattice expansion will be also there, okay. So if resistance will be changed, so that's why as soon as we expose to the hydrogen gas, its resistance will be increased, okay. So that is the case. So suddenly we have well separated nanoparticle, and as soon as we expose to the gas, then resistance will be increased. But if we will inject the hydrogen up to a certain quantity, so after that, you know that lattice expansion will be there, and then this palladium will be absorbed the hydrogen, and as a result of that, there will be swelling will be there in these nanoparticles, and due to this swelling, these well separated nanoparticles, they will connect to each other, and once they will connect to each other, you know the palladium is a metallic system. So as soon as they will connect it, its resistance will be decreased. Okay, so that's why we will see this type pulse-like response. So, and this one is we switch off the gas. Okay, so this particular one connected here, like it is shown here. And as soon as again we remove the gas, so then as we remove the gas, then again the lattice contraction will be there, and as a result of that, particle size will be again decrease it. Okay, so there is slightly decrease it. So then this will be particle will be well separated. Okay, like this one, and then again we will further remove it, and then it will show like this type of behavior. So this type of pulse-like response has been observed in case of the nanoparticle, and due to this pulse-like response, that response time of the palladium is very short. Okay, even people have reported like less than 1 second or like that one also. Okay, so that is the case of the palladium nanoparticle. But in case of the palladium nanoparticle, like other system, it have some issues. So main issues with the palladium nanoparticle is that because they are free-standing particles, so they will degrade with time due to highly active surface area. So that's why if we will make a sensor using palladium nanoparticles, so its performance will be degrade with the time due to oxidation of the surface, oxidation of the particle or like that one. Then another thing is that adhesivity on the surface of this palladium nanoparticle is also not good. And most important thing is that in this case, like in case of the palladium thin film as well as palladium nanoparticle, we have taken 100% palladium. And palladium is just like gold, it is a very expensive metal. So that's why, and you know that we need to reduce the cost of these sensing materials. So that's why we have decided to work on this palladium-based nanocomposite material. So what is this nanocomposite? So basically, nanocomposite is it is like consists of the two phase. So we can say it is mixture of the two phase. So in that case, dimension of the one phase should be less than 100 nanometer. So in that case, we can say it is like a nanocomposite. So in this case, we have selected, so there will be two phase will be there. One phase will be for metals, and another phase can be a matrix, or we can say like that one. So what is the role of the matrix that we have seen from our previous slide like that? First thing is that it should able to protect the nanoparticle from the oxidation. Okay, so it will either it will cover the particle or like that one. And another thing is that if I will deposit palladium or any metal nanoparticle on a substrate, so as we increase the thickness or the particle, so then these particle will combine together and they will form the bigger particle. Okay, and you know that we have seen our requirement is that the particle size should be as low as possible, and it should be order of like less than 5 nanometer, like that one. So to prepare a nanoparticle of very small size, it is very difficult because they will combine together and they will form. So if we can put these particle in some matrix, in that case, we can able to restrict the size of these particles. So now question is coming, what type of material that we can take for the matrix? So the choice that we have is carbon, silicon, silica, and aluminum dioxide. Okay, so these different material we have selected it due to their some good properties. Because why we want interested in silicon is because already industries is silicon technology is well established and it will be easy for integrate in the IC technology or like that one. But the problem with the silicon is that palladium form silicide. Okay, so that's why it will form a alloy, palladium silicide alloy. So that's why it is not useful. Then in case of the silica and aluminum dioxide, again the problem is that oxygen is there. So again there is chances of the oxidation of the palladium. So that's why we have synthesized these type of sample, but then we found that some oxide peak is observed in case of the X-ray diffraction pattern. So then we finally selected the carbon, and then why? So because carbon have some important thing like that, it does not form any alloy with the palladium. And another thing is that there are some theoretical studies in that one. They have tried to explain the phenomena of the palladium hydride, and in that one they mention like that carbon can also play important role, and that is mainly these paper are related to the oxide paper. So in that one it has been mentioned like that one palladium, this carbon can this hydrogen can spill over on the surface of the this carbon, and that can also able to increase its sensitivity or like that one. So on the basis of that we decided to take carbon as a matrix. And another thing is that carbon surface has a very weak interaction with the metal particles on spotted on this thing. So now how we can synthesize these nano composite. So for that technique that we have used is a atom based sputtering. So this is a modified sputtering system that rather that is being used as a RF sputtering like that one. So what modification that we have done, because in this case like that this one is target we have taken graphite target of the 2-inch, and on that one we have pasted this palladium foil. Okay, and then like that one though, so then we simultaneously sputtered out this one. So the palladium and carbon from the graphite, they will come out simultaneously and they will deposit on the substrate, and that way it will form the. So it is very simple technique. And only thing that modification that we have done is instead of taking this ionized plasma, we have used a neutral plasma in this case. So we have created the plasma of the argon gas, and then there is a electron source is there. So that will supply the electron, and that way we will create the neutral argon atom, and then these neutral argon atom we will bombarded on this one, and that way we able to create the nano composite. Okay, and then another beauty of this technique is you can able to change the composition of these materials, like how much area that I am covering with the palladium, that will decide my composition. So for example, if I want to put very small quantity, like 5% palladium, I can put it on the surface, or 10% area I will cover with. So that way I can able to change the composition and as well as the size of the particle also like that one. So theoretically there is report is like that one, if the concentration of the palladium is more than 30%. So in that case, these will be form a agglomerated of the particle. So that is basically sorry, not 30-40% is a percolation limit. So in this case, we want to study the effect of the percolation also in this case. So we synthesize two set of sample. So in this case, in one case we have taken concentration of the palladium is less than 40%. It was roughly around 20% or like that one. And another one we have taken around 50%. So that was our case. Okay, but you know that this sputtering rate of the carbon and palladium, they are different. So as a result of that, it is very difficult to control the exact composition of the palladium and carbon in this type of system. but that doesn't make very important for us, because our main concern is that one sample should be below percolation limit, another one is above percolation limit, or like that one. Okay, so to identify the concentration of this material, we have used Rutherford backscattering spectrometry. So it is again a accelerator-based technique. So just for student, I will briefly explain how does it work. So you can take a high energy 1.7 MeV helium beam, and that you bombard on a substrate like that. This is my palladium carbon nanocomposite substrate, and then backscattered helium, same helium ion will be backscattered, and that I will detect it. Okay, so ideally this one scale should be up to 1.7 MeV. So if a same backscattered helium ion is coming, okay, so I got these type of peak, and then we have fitted it, and on the basis of that we calculated the thickness of the film, and as well as the composition of film, means how much is carbon in this one and how much is palladium in this one. So in our case, like that sample A is concentration of the palladium is around 25%, and in another one is around 45%, or like that one. Okay, so this one is the transmission electron microscopy image of this one. So PC25 means in this case concentration of the palladium is 25%, and in this case it is about 45%, or like that one. So here you can see the scale bar is about 10 nanometer in both the cases. They are on the same scale. So here you can see the particle size is about between you can say 4 nanometer, or like that one. And in this case you can say these particle size combined together and they will agglomerated, because in this case concentration is more than 45%, or like more than 40%, or like that one. So these are the scanning electron microscopy imaging. Just we expose the sample to 2-3 times, like not 2-3, like 20 times, and then after that, just I want to check it out how its surface morphology is. So this is a pristine sample, and this one is sample that is exposed to the hydrogen gas with the many cycles. So there you can see like that one. So that hydrogen is it will uh, uh, it will hydrogen will inject in the film, and then and in some cases like that you can see it can also form like bubble like structure will be also formed. So it is quite possible like that one. Hydrogen is not only not only sitting in the interstitial position, but it may be possible like that it can also sit at the interface between palladium and silicon substrate, and as a result of that we have observed like that this film is peeling off after like 30 cycle, or like that one. And this one is synchrotron diffraction data of the pristine, and then we expose to the hydrogen gas, and then again we have done it. So this sample is PDC 45. So there we can see this crystalline size is again we have changed on exposure to the hydrogen gas, like it is changing from the 2 to 4 nanometer, like that one. And again we also found like it on exposure to the hydrogen some strain is also created. And this one is a setup that we have used for, so this is a our indigenously fabricated gas sensing setup at our laboratories. And with help of these sensing setup, and then we write program for this IV and CV, IV. And so this type of response curve that we got it. So this is the effect of the pressure. So we have started with the 5 millibar, 10 millibar, 20, 30, 40, 50. So different hydrogen pressure that we have exposed to the material. And at each time we record the sensing response for the PC25 as well as PC45. So what we have observed is like then this is fast. So in case of the PC25, that response time that you can see it is very sharp. So that we found is 5 seconds. Okay, so and in case of the PC45, the response time that we got is around 30 seconds. So if I will compare with the thin film, so this one is better than the thin film, but it is worse than I can say the nanoparticle. Okay, and yeah, same thing like this one is same order of that case of the palladium thin film. So main reason is this case in this case, concentration of the palladium is very high. So they are percolated it, and we can say it is just like a continuous film in this case. Then we calculated the response time, recovery time, and sensitivity of this type of material. And then you can see this response time is also depend upon the pressure, means at what pressure that we are exposing it. Okay, so like in this case, you can see at a 500 millibar. So this one is red curve is for PC25, and this black curve is for PC45. So there you can see response time is, I already mentioned, it is quite low, and here it is about 30 seconds or like that one. And same thing for the sensitivity, you can see at this pressure, you can see the sensitivity is relatively very high in case of the palladium nanoparticle having smaller size, and in case of the percolation, the sensitivity is same like 5% that we have seen in case of thin film. So that way we can say with the help of the nanocomposite, our response time is almost similar like a nanoparticle, but we can able to enhance the sensitivity, and same thing for the recovery time also like that one. So our recovery time is that is not as good, because it is your order that you already value, you can say it is like 200 seconds or like that one, but still it is relatively good if you compare with the other methods. So what is the mechanism and how we can explain to this thing? Because we have seen this response time and sensitivity, they also depend upon the pressure, means at the low pressure, you can see the response time is different. At a high pressure, like 500 milliwatt, is different. So to explain that, we have used the same explanation that has been used for like palladium thin film and palladium nanoparticle. So in that one, I explain you like this palladium nanoparticle or thin film. So hydrogen will work as a catalytic, and so that will dissociate the molecular hydrogen into atomic hydrogen, and that will be absorbed. So in addition to that, here carbon is also playing important role, because these nanoparticles are embedded in the carbon matrix. So we have propose a three-step mechanism in this case. So first is activation and dissociation of the hydrogen molecule on catalytic metal side. So it will be done by the palladium. So palladium will dissociate hydrogen into atomic hydrogen on palladium surface, and then transition of the atomic hydrogen across the palladium carbon interface, or diffuse the hydrogen at the core of the palladium. So once it is in a atomic hydrogen, there are the two chances. So either hydrogen will be go and diffuse inside this palladium nanoparticle, or it may be possible like that this atomic hydrogen will spill over to the carbon surface, and then on the carbon surface it will absorb it and it will migrate it. Okay, so that's why you can see when we are removing the hydrogen in this case, because you know that carbon have a very weak interaction with the palladium, uh, uh, a weak interaction with the hydrogen. So that's why when we are removing the hydrogen, we can easily able to remove it. Okay, so that we have explained like at low pressure. So size will be more, because in case of the concentration of the palladium is less than threshold, like in PC25. So in that case, at low pressure, size will be dominated over the spillover, and at a high concentration, this will be reverse effect will be there. Same thing for the high pressure, like at 500 or 1 atmosphere. So in that case, size will be play critical role. Like size, the greater the size, means effect will be the size, and spillover will be less effect or like that one. Okay. So in summary, I can say like that one, this one is palladium thin film. Here response time is between 15 to 20. In case of the palladium nanoparticle, between 2 to 3 seconds. And in case of this palladium nanocomposite, we can say it is about the 5 second, like if the concentration is below percolation limit or like that one. So if I will compare this palladium composite system with the other system, so most important thing is that that sensor that we can fabricate using this one is it will work at the room temperature. So it is not like that tin oxide that will work as a 200 or 300 degree centigrade. And we have also checked the repeatability. So up to 30 cycle, it can work very well. And since we have replaced palladium with the carbon, like only a small quantity, like only you can say like 20% palladium we are using in this case. So 80% palladium we have saved by using palladium nanocomposite. Okay, and in comparison to thin film, our response time is quite good, and it has a better lifetime, because in this case of the composite palladium, they are embedded in the metric, so they will be not exposed to the like oxygen, or so the chances of the palladium oxidation is relatively low. Okay, so finally I can summarize my talk. So I can say like that nanomaterials such as a nanoparticle and nanocomposite offer a great promises for enhancing the performance of the gas sensing of these devices. And such nanocomposite based sensing devices are expected to have a major impact upon the generation, transportation, and leak detection of the hydrogen driven vehicle. So these are the few papers that we have published. This one is related to that work that I already communicated it. And then these are the other papers that is either related to the this palladium nanoparticle or palladium thin film, or few of them are how to prepare the thin film by using that EVM setup. So finally, I would like to acknowledge my seniors, Professor B.R. Mehta, and Professor D.K. Awasthi, Professor Kanjilal from IUAC. And that work, it is funded by DST-SERB, and this work has been carried by Dr. Mohit Kumar. And I also like to acknowledge IUAC, because all the work I have carried out at IUAC only, and I also like to acknowledge JNU. So thank you very much, and Jai Hind to all of you. Yeah.
Yeah, thank you very much, Professor Pawan Kularia. And now I request Nipun, can you take few questions from the chat box? Or the participants, they want to ask this one directly, you can unmute them.
Yes, sir, we can directly ask participants, because as of now, I could not find any question in the chat box. Only, yes.
Yeah, we have time, so.
Yes. May I request anybody from the audience if wants to ask directly, they can please raise their hands. I will unmute them.
So it means either everything is well understood,
Yes.
or.
No, sir. People, I mean, audience is saying that it was such a wonderful talk. They are praising, sir. Yes, we have a first question from Miss Sonam. She is asking why palladium is the best hydrogen absorbent.
Yes. So because there are few things that I already explained. First thing is that it is showing some catalytic response. Okay, so it have a very low activation energy to interact with the atoms of the hydrogen. Okay, and another thing is that it can dissociate the hydrogen, so that's why it can be easily absorb that atomic hydrogen inside this thing. And another thing is in the palladium is that if you can see its phase diagram, so it is PDH2. So it means it can able to absorb 200% of the hydrogen inside its lattice, and that is main reason is the size of the hydrogen is very small. So that's why palladium lattice have a phase center structure, and in that one lot of space is there, so hydrogen can easily go and inside that interstitial site in that one.
Thank you, sir. I hope Sonam has got a response. We have another question from Mr. Sumit. He's asking, are platinum nanoparticle based hydrogen gas sensors are selective to hydrogen, or they have selectivity to other gases also?
For platinum I think platinum, I am not sure, but that selectivity portion, I think platinum will not show. So in most of the sensing material that you will find, people are using palladium only, because if we will consider other property of the platinum and palladium, so both of the noble metals, and they will show almost similar properties. But the only property of the better property of the palladium is that it is showing this catalytic response, means dissociation of the hydrogen, molecular hydrogen into the atomic hydrogen. Okay. So due to that dissociation property, it is showing this selectivity. Okay. So in case of the platinum, I have doubt whether it will be dissociate the.
Sir,
Yeah.
sir. Yeah, sir. He was asking specifically about palladium.
Palladium.
Yes,
Okay.
yes.
Yeah. So palladium
Like-
is, yeah, palladium will not select any hydrogen gas, other gas. So like if palladium will be exposed to the simultaneous like hydrogen, nitrogen, oxygen, and ammonia, so palladium will only select the hydrogen. It will not interact with anything. So that we have tested it like that one. We we make a device, and same device we expose to the nitrogen gas. And in that case, that change in the resistance that we observed, it is hardly normally it is around 50 ohms. So it is increased to 51 or 52 ohm, like that one only. Okay. So
Thank you.
yeah, yeah.
Thank you, sir, for clarification. We have one more question from Dr. Bharti Patil. She's asking, sir, suppose if I am having my sample powder and wish to check its gas sensing property. Okay. This is not a relevant question, sir. I'm well, sir.
No. Suppose if you have powder samples, so then you can make the pellet.
No, sir.
Okay, yeah. So, or either you can do some spin coating, and by which you can make the film, and then you can do the sensing response of that one.
Sir, we have another question from Dr. Debanjan Acharya.
Yeah.
He's asking, what about the long-term study of palladium, as oxidation of palladium is inevitable?
Yeah. So that is the beauty of the palladium, because only problem with the palladium is its cost, because most of that oxide that you will see, like titanium oxide, tin oxide, or this thing, so they are very cheap material, and palladium is a highly costly material, very expensive. So that is the only problem to use palladium for this type of gas sensor or like that one. Okay. Otherwise, palladium have all good characteristics that is required for a particular gas sensing applications. So that's why there could be approach like that we have used to use this nano composite. So in that case, we can able to reduce the that amount of the palladium that is very required. So like we have tested only this one for 25% atomic percent concentration of the palladium. But if a person can tune this one, like it can reduce to 5 or like that one. And if at 5% concentration, if you can get a good response, then definitely these palladium based nanoparticle or composite can be used for the industry.
Yes, he's also curious about the humidity influence.
Humidity, it will not affect it. Yeah. Because palladium is metals, and that way it is in bulk case we have tested it, so it doesn't interact with the water or like that one. But because it is a normal metal, like in case of the gold, you know it, because gold will not interact with the water or like that one. But that testing we have to done it. We have not done it, but I am sure humidity will not affect to this material.
Okay, thank you, sir. We have another question from Mr. Amit Kumar Shringi. He is asking how you manage the palladium nanoparticles using sputtering with carbon at the same time.
Yes, that's why I mention in this slide, because here we are using this one atom beam sputtering, not a RF sputtering. And in case of the sputtering, you know that this rate of the deposition or sputtering rate it is different for different element. Okay, so sputtering rate for palladium will be different and sputtering rate for the graphite will be different. So that's why that composition that we are expecting, so that we didn't get it. Like, so in case of like in one case, I was expecting 50% area, I covered it. So if the sputtering rate of the both the element is same, so in that case, it's supposed to be exactly 50%, but from the RBS, we got it is around 44% or like that one. Okay, but with iteration, one can able to tune it because it is not a complex system. You only two system is there, palladium and carbon. So you can do five, 6 experiment. You can do it, and on the basis of that, you can do RBS or this EDEX. You can do it, and on the basis of that, you can analyze it. Means what is the sputtering rate of the palladium and what is the sputtering rate of the carbon or graphite.
Thank you,
But-
sir. I hope.
Yeah. Yeah.
Yes, thank you, sir. I hope Amit is clear. We have another question from Mr. Javed. He's asking which type of material properties mostly we have to focus to develop a sensor for hydrogen, and please discuss the stability and working cycle for palladium.
Yeah, for stability or this thing for palladium thin film, people have used for more than 100 cycle or like that one. In case of this palladium nanocomposite, I have tested for 30 cycle, and after 30 cycle, we have observed there is a cracks in the film, or sometimes film will peel off. Okay, but in case of the thin film, it have very good cyclability. Regarding other stability means like humidity and all that earlier participant has also asked, that we have not tested it, but definitely in future we will do it. Yeah.
Okay, thank you, sir. So one of our participant wants to ask you question directly. I will just unmute him.
Yeah.
Hello, Mr. Sudhir.
Yeah.
Yes, please go ahead.
So, is there any relation between DC conductivity or AC conductivity for the sensor properties, response time and so? Hello?
Yeah. So basically, what device that we have used, we have simple use like DC resistance, we have measured it. Okay, but I think in case of this type of material, it doesn't matter is because normally what we are doing is we are not using any capacitance in this case. Okay, so
Yes.
just it will just work as a metallic conductor, and then we are measuring its resistance. So yeah, so that way I think it doesn't matter it like that one. That
Particularly dielectric properties are having any relation between this sensor properties of the sensors?
Dielectric property will be if you will because the sensor that I designed, that is metallic sensor. Okay, but in case of like someone is working on this oxide, so in that case I have doubt like dielectric is basically charge separation. So how they measure it, because I am not working on oxide based sensor. So best thing is that person who is working on these oxide type of materials. And another thing is that like this in oxide sensor, how they are detecting the sensing behavior, because there are various ways by which we can measure the sensing response. Like in metal, it is very easy to detect the sensing response just by measuring the resistance. But there are some material, they are emitting light when you expose to the hydrogen gas, or they change the color. Okay, so if something is like that one, in that case, dielectric response will be definitely moderate. Yeah, because if band gap change is there or like that one. Yeah.
And second thing which I have observed, that all the these sensors which are mentioned in this 4-day lectures, they are just simple elements, and there is no any compounds, or there is no any alloys involved in it. So what might be the reason? It's most the simple will be the metal that will be response more will be or something else.
Yes. So main thing in this type of sensor is because we want sensitivity of the sensor should be very high.
Yeah.
Okay, then it will be easier for us to detect the signal like that one. So normally if it is a metal, then suppose for example, like if resistance is 50 ohm and then it will change to 500 ohm or like that one. Okay, so 10 times it is increasing, so we can easily detect the signal. So for example, if we make the alloy, so you know that if we make the alloy, then its conductivity will be decreased. So if
Yeah.
conductivity will decrease, then it will due to some additional scattering will be from that element that is present like that one. So if the resisting conductivity will decrease or resistance will be very high, so in that case this sensitivity will be decreased. Okay.
Okay.
So that might be the reason that people are not using alloy for this type of application.
Okay. Okay.
Yeah.
Thank you. Thank you, sir.
Thank you, sir. I guess we are done with question and answer. I could not find any other query from participant. With this, may I request Professor Mahesh Kumar to kindly present vote of thanks to Professor Pavan Kumar Guleria, sir, and conclude today's session with his closing remarks. Thank you, sir.
Yeah, let me thank Professor Kuleria for his excellent talk. And participants were waiting from, I think, from last 3 days about this hydrogen sensing. So I'm sure now their doubts are clear. And thank you, Professor Kuleria, for accepting our invitation and delivering this excellent talk. With this, we will close today's session. Yeah, thank you very much.
Yeah,
Sir,
thank you very much. Yeah.
Sir, we have one last doubt that has just come up from Dr. Bharti Patil. She's asking what was the resistance value in your case?
So in my case, it is around 50 ohm that I mentioned it like that one. So 50 ohm was when it was a percolated film. But in this another case, it was relatively high. Exactly, I don't know. But in percolated, it was 50 ohm, like PC45 sample.
Yeah, so in
but you can. Yeah, you can see that paper that I mentioned it that has been already published in International Journal of Hydrogen Energy in 2017. So please go through with that article, and if something is not clear, then I will be happy to explain you. Yeah.
Yeah, thank you, sir.
Yeah, I would like to mention here because in the metallic and this metal oxide difference is there in the metallic because resistance is less, 50 ohm is there. So we can apply even less voltage. So basically these are the low power devices as compared to the metal oxides. So this is one advantage of palladium based hydrogen sensor as compared to the metal oxides.
Yes, exactly. Yeah.
Yeah. So with this, we will close this one, today's session. And thank you very much to all the participants and the speaker and Nipun and team. They are managing from the whole day this one. So thank you all. Yeah.
Thank you, sir.
Yeah. See you.
Thank you. Namaskar.
10 a.m. Yeah. Okay. Okay.